In our study of trigonometry, one of the first things we'll need to be comfortable with is drawing angles in standard position. We're going to start by learning what standard position is, and we'll go ahead and start with degree measure, which is something we should be familiar with from geometry. So we're going to draw a coordinate system. An angle that's drawn in standard position will have its vertex at the origin, and its initial side will be on the positive x-axis. And then we're going to rotate the positive x-axis, whatever the size of the angle is, and this will be the terminal side of the angle. Notice that I've drawn this angle in a counterclockwise direction. This angle, which we'll call theta, has a positive measure. If I start with my terminals, we'll start with my initial side on the x-axis and I rotate in a clockwise direction, then my angle will have a negative measure. So let's draw a couple of angles in standard position. We're going to start with 120 degrees. Okay, so this is 0 degrees. If I rotate the positive x-axis one complete revolution, how far around would that be? 360 degrees, right? Okay, so if I do half of a revolution, that'd be 180 degrees, and I think I'm going to label this for you on our original picture. So all the way around is 360 degrees. Halfway around would be 180. So a quarter of the way around, 90 degrees. Okay, so this must be 270 degrees. Okay, that mental picture is going to help us to decide where to draw 120 degrees. So we start on the positive x-axis. If we go this far, we've gone 90 degrees. We need to go about 30 degrees more. So this is my angle theta. And notice how the terminal side lands in quadrant number 2. Now let's try another angle. Let's go with 400 degrees. Okay, so what do you notice first? It's more than 360 degrees, right? So that means that I start my initial side here on the positive x-axis. I have to go 360 degrees, takes me to here. How much is left to get to 400? Right, 40 more degrees. So this is 400 degrees drawn in standard position. Now let's try one that's a negative angle. Let's do theta equals negative 200 degrees. Negative angles go, and we want to rotate the positive x-axis in a clockwise direction. If I go halfway around, that's negative 180 degrees, so I need to go just about 20 degrees more. It'd be about right here. Let's look at the angle theta equals negative 270 in degrees. So we start with the initial side along the positive x-axis, and we're going to rotate 3/4 of a revolution. And this is our angle negative 270 degrees. Okay. Notice that there are a lot of angles whose terminal side would be in exactly the same place. In particular, there's an easy one to spot. 90 degrees in the positive direction. Has its terminal side in exactly the same place. Are there other angles? Yes. For instance, suppose that we went in the negative direction completely around, that would be negative 360, and then went negative 270 more. That's going to be negative 270 minus the 360, that would be 630 degrees negative. That angle, all the way around plus the negative 270, also has the same terminal side. Okay? And you can see I could go around 2 complete negative revolutions and then stop at negative 270. And I'm going to get yet another angle with exactly the same terminal side. Okay? Don't like negative angles, we can go the other direction. Suppose that I have the 90, I can make a complete revolution all the way around, 360 degrees plus another 90. I'm going to stop in the same place. Or I can make 5 revolutions around and then 90 degrees more, and again I'm going to get a terminal side in exactly the same place. These are all examples of coterminal angles. They have exactly the same terminal side, the same starting point, but they have different measures. We need to practice finding coterminal angles to help us with our study of trig. Often it will be helpful to be able to find specific coterminal angles for a given angle. And let's look at some examples. We're asked to find 2 positive angles and 2 negative angles that are coterminal with the given angle. Let's start with 210 degrees. This angle is already positive. I know for sure that if I add 360 degrees, it's adding 1 revolution on my angle, I will have the same terminal side, and it's still going to be positive. So this is 570 degrees, and this is a positive angle that is coterminal with 210 degrees. Okay. If I add another 360 to this, then I'll get 1 more revolution on my angle and a bigger angle that lands in the same, has the same terminal side. So this is 720 plus 210. It's going to be 930 degrees. Okay, and yes, you could have just added 360 to this one, you get to the same place. Okay, well I have enough positive angles, so let's try to get some negative angles. What happens if I subtract 360 degrees from this angle? Okay, so I subtract this, it's negative 150 degrees. There's 1 negative angle that is coterminal with my given angle. How do I find a second one? Right, subtract another 360. You can subtract 360 from the negative 150, or you can 210 degrees minus 2 times 360 will give you the same result. Okay, let's look at negative 100 degrees. What happens if I add 360 to this? Because remember, coterminal angles just differ by multiples of 360 degrees. So let's take negative 100 degrees and add 360 degrees to it. 260 degrees. Okay, and that's one of the positive angles that I need. Now let's get another positive angle by adding 360 degrees one more time. Okay, and you can see that if I do negative 100 degrees plus 3 times 360, I'm just going to get yet another bigger positive angle, and that's not what I'm asked to do. I need to look for some negative angles. So now let's go back to our negative 100 and subtract. We'll subtract 360 degrees one time. This is negative 460. Can do that. Subtract 360 again. And I've satisfied the requirements of the problem. I found 2 positive angles that are coterminal with negative 100 degrees and 2 negative angles. I'd like for you to put a little star by this one though, because as it turns out, this 260 degree angle is very important to us. It is the angle of least non-negative measure that is coterminal with the given angle. It's so important, we're going to give this the name theta c. All right, we have one more example. 700 degrees. What do you notice about this one? It's bigger than 360. Okay, so certainly if I add multiples of 360, I'll get bigger positive angles, and that's fine. But if I subtract 360, I'll get a positive angle there too. So let's go ahead and start with that. That's 340 degrees. Okay. So there's one positive angle coterminal with my given angle. Let's subtract 360 again. So we're subtracting two 360s. That's negative 20 degrees. Okay, so to get another angle, you can see that I'm going to need to subtract another 360 from that. And I'm going the wrong direction now, right? The instructions were two positive angles and two negative angles that are coterminal with my given angle. So how am I going to find that other positive angle? So we can go back here to the 700 and add 360. Often we'd like to be able to find the angle of least non-negative measure that's coterminal with our given angle. And remember, we've called this theta C. Let's try that for negative 765 degrees. The first thing we notice is we're looking for a non-negative measure, and we have a negative angle. Okay, coterminal angles, remember, differ by multiples of 360 degrees, so we can simply start by adding 360 degrees to this and see what happens. What size angle do we get? Negative 405 degrees. That's more than one revolution, right, in the negative direction, so that's not enough. Let's take negative 765 degrees plus 2 times 360. So that would be negative 765 degrees plus 720 degrees. It's negative 45 degrees. Unfortunately, it's still negative. So we just go again. Okay, so negative 765 degrees plus 3 times 360 degrees. That's going to be 360 degrees more than this angle, and that would be 315 degrees. So this is theta C, the angle of least non-negative measure coterminal with our given angle. All right, let's try this again for 1180 degrees. All right, this is a positive angle, a really big positive angle, right? So we need to subtract multiples of 360. Now I could start with the subtracting 360 degrees, but I can tell that's not nearly big enough. So let's try 1180 degrees minus 2 times 360. That's 720. Well, that's only 460 degrees, and that's still more than one revolution, so that wasn't enough. Let's try 1180 degrees minus 3 times 360. That's going to be 360. Less than that is 100 degrees. And that will be our theta C, an angle of least non-negative measure coterminal with our given angle. We're all pretty comfortable with degree measure for angles, but in our study of trigonometry, we'll find another measure for angles that's even more useful, and that's radian measure. So let's start by defining what a radian is. So we start with a circle of radius r, and we've drawn a central angle theta that intercepts an arc of length r. All right, so that means that the arc is the same length as the radius of the circle. In that case, theta is an angle of measure 1 radian. It would be helpful to know how many radians are in one complete revolution, just like we know there were 360 degrees in a complete revolution. So how do we figure this out? Well, one complete revolution is the same length as the circumference of the circle. Do you remember the formula for the circumference of a circle? Yes, 2 pi times the radius. Okay, so how many r's are there as you go around the circle? Well, there are 2 pi r's as you go around the circle. So one revolution is 2 pi radians. Okay, now just like in degrees, you notice that if we want to know a quarter of a revolution, a half of a revolution, 3/4 of a revolution. So let's write those down. 1/4 of a revolution. We'll come back to that one. Let's do half of a revolution first. half of a revolution is half of 2 pi. That one's easy, pi radians. So a quarter of a revolution is going to be half of that, or pi over 2 radians. And 3/4 of a revolution is 3 pi over 2 radians. Okay. And I want you to get used to those on your coordinate system, because our next step is to draw angles in standard position given a radian measure. Let's look at drawing angles in standard position when the angle is given in radian measure. Okay, so it'll be helpful to remember that a quarter of a revolution is pi over 2 radians, that half of a revolution is pi radians, and 3 pi over 2 radians. In standard position, we start with the initial side on the positive x-axis, and counterclockwise is for positive angles, clockwise rotation for negative angles. That hasn't changed. Okay, so pi over 6. It's positive. That's a good start. Okay, pi over 6. It's a lot smaller than pi over 2, right? Okay, so in fact, it's 1/3 of pi over 2, so it should be about 1/3 of the way into the first quadrant. Okay. Now let's look at 2 pi over 3. Okay, well, it's not quite all the way halfway around, because halfway around would be 3 pi over 3. I haven't quite made it that far. In fact, I've made it 2/3 of the way. So 2/3 of the way, 2/3 of halfway would put 2 pi over 3 approximately here. Okay, 9 pi over 4. Well, 9 pi over 4, it's a really big angle compared to the other two we've looked at. In fact, let's think of, what if we went a complete revolution? We know that that is 2 pi radians, but how much is that in pi over 4s? How many pi over 4s would that be? It would be 8 pi over 4. Okay, so keeping this in mind, when we look at the 9 pi over 4, it's 8 pi over 4 plus another pi over 4. That means it's a complete revolution in the positive direction plus another pi over 4. And that pi over 4 is half of pi over 2. So here's 9 pi over 4 in standard position. Negative 6 pi. So first of all, I notice I need to go in the negative direction. If I go around one complete revolution in the negative direction, that's negative 2 pi. This would make negative 4 pi. So negative 6 pi is 3 complete revolutions in the negative direction. So let's look at negative 7 pi over 12. It's going to go in the negative direction. And how far? Well, halfway around would be negative 12 pi over 12, so we're not nearly that far. Is it a quarter of the way around? So that would be negative 6 pi over 12. Well, it's just a little bit more than that. Later on in this video, I will show you how to convert between radian and degree measure, but you'll notice that I did all of these without ever doing that conversion. It's in your best interest to learn to think in radians and be able to appropriately place an angle in standard position without having to convert everything back to degrees. Let's look at finding coterminal angles using angles given in radian measure. We've previously seen that coterminal angles differ by the number of revolutions or the direction of those revolutions. So in degrees, we added or subtracted multiples of 360 to find coterminal angles. So what should we do when we're faced with angles in radian measure? Right, we're going to add or subtract multiples of 2 pi. Okay, so let's start with this angle, 3 pi over 4. It's already positive, so one way to get positive angles coterminal with it would be to add multiples of 2 pi. So if we start with 3 pi over 4 and we add 2 pi, Now we're going to need to think of this with, a common denominator. So 2 pi is the same as 8 pi over 4. So this is 11 pi over 4. Okay, if we take 3 pi over 4 and we add, instead of 2 pi, we're going to add 2 pi's, or 4 pi. So again, we need to think in terms of a common denominator. This is 4 pi. How many fourths is that? 16 pi fourths. Okay, so we add this 19 pi over 4. Okay, that takes care of the 2 positive angles that I needed. Now let's look for some negative angles. So we can take our 3 pi over 4 and let's try subtracting 2 pi and see what happens. Now remember, we said 2 pi can be written as 8 pi over 4. So that's what we need to be able to do the subtraction. And this gives me negative 5 pi over 4. So I've subtracted 2 pi one time and I have one of my negative angles that's coterminal with 3 pi over 4. Let's subtract another 2 pi. Okay, and so that's 4 pi here again. That's the same as 16 pi over 4. And a second negative angle coterminal with 3 pi over 4 would be negative 13 pi over 4. Let's look at this next angle, negative 20 pi over 3. Okay, well, it's already a negative angle. It's more than one revolution in the negative direction, isn't it? So we're going to have to work a little bit harder on this one. Let's go ahead and start by trying to get to some positive angles. I'm going to add 2 pi to see what happens. Okay, well, now this is thirds, so I want negative 20 pi over 3 plus 6 pi over 3. So that's negative 14 pi over 3. That'll take care of one of those negative angles. And we're going to just keep adding multiples of 2 pi. Okay, so this is 4 pi. How can I write that with a denominator of 3? Right, 12 pi over 3. Okay, negative 20 pi over 3 plus 12 pi over 3 is negative 8 pi over 3. It's yet another negative angle that's coterminal with my given angle. And I'm still in search of positive angles. So we're going to add another 2 pi. All right, this is 6 pi. So how's that written with a denominator of 3? Okay, 18 pi over 3. One thing you should notice at this point is that sometimes it's not obvious how far you have to go. But the more you practice with radians, right, we're still looking for a positive angle, and we're not there yet. The more you work with radians, the more you might be able to sort of skip some of these steps and go a little faster. Okay, but it's getting better. This is less than one revolution, so the next time I add another 2 pi to that, I should come up with a positive angle. So 8 pi. I'm going to have to write that with a denominator of 3. That's going to be 24 pi over 3. Okay, finally I found a positive angle coterminal with a given angle. And just remember earlier we talked about theta c, the angle of least non-negative measure that is coterminal with our given angle. And we're going to have to practice finding that using radian measure as well. So this is the first one we've seen. Okay, if I add 2 pi one more time. This is 10 pi, so written with the denominator of 3, that's 30 pi over 3. And this is 10 pi over 3. So when I go to type in or write down my answers, I found 2 positive angles that are coterminal with my given angle. And then I found 3, so pick 2 of these, and there are your answers. In this example, we're asked to find the angle theta c of least non-negative measure that is coterminal with the given angle. So we'll start with negative 5 pi over 3. Since it's a negative angle, we're going to try adding 2 pi and see if that will give us our theta c. Okay, so 2 pi written with a denominator of 3 is 6 pi over 3. It's negative 5 pi over 3 plus 6 pi over 3 is pi over 3. That's certainly a positive angle, and it's the smallest one that is coterminal with negative pi over 3, so we can call this our theta c. Now let's look at 29 pi over 6. It's a positive angle, so we should probably start by trying to subtract some multiples of 2 pi. 2 pi is the same as 12 pi over 6. So just subtracting 2 pi one time won't do it. In fact, I should be able to subtract it twice, and let's see where that gets us. 29 pi over 6 minus 24 pi over 6. Remember, this is 2 pi twice, or 4 pi. Okay, so when I do this subtraction, I get 5 pi over 6. That is a positive angle. It's less than 1 revolution. In fact, it is the smallest non-negative angle coterminal with the given angle, so let's label that theta c. Let's look at how we can convert between radian measure and degree measure. So previously we've said that 1 complete revolution is 360 degrees. We've also said that 1 revolution is 2 pi radians. Okay. So that means that 2 pi radians equals 360 degrees, or if we divide both sides by 2, we find that pi radians is 180 degrees. Notice that on the pi I did not put any sort of symbol. That's because typically radians don't have a symbol, and it's understood to be radians if it's not written there. Therefore, it's very important if your angle's in degrees that you actually use that degree symbol. Okay, this is all we need to know to be able to do the conversions, so let's look at some examples. Let's convert each of the following from degree measure to radian measure. So we'll start with 30 degrees. Since pi radians is 180 degrees, we can multiply by the fraction pi over 180 degrees. This is equal to 1, so we're not changing the value. And the degree units will sort of go away and leave us with radian units. We want to reduce the fraction. 30 goes into 186 times, so this is pi over 6 radians. Negative 240 degrees. Okay. So again, pi radians is equal to 180 degrees, so we can write this ratio, multiply. It's a little bit trickier to simplify this one. This is negative 240 pi over 180, and you need to reduce that to lowest terms. So let's see, if we divide by 6, that would be negative 4 pi over 3. The last one is 160 degrees. So again, we're converting degrees to radians. We're going to multiply by pi over 180 degrees. We can divide the numerator and the denominator both by 10 to get 16 pi over 18, and then of course we can reduce that a little bit further to get 8 pi over 9 radians. Let's convert each of the following to degree measure. So this is 13 pi over 6 radians, and I know it's radians because no unit is given, and I'm told to go to degree measure. Okay, so what should I multiply by? It's still true that pi radians is 180 degrees, but if I multiply by pi over 180 degrees, that won't make any sense, will it? Because I won't end up with the units of degrees that I want in the end. So instead, we want to multiply by 180 degrees over pi. We're going to end up with degrees in our answer. All right, well, the nice thing is that our pi's divide out. And what do we have left? Well, we have to multiply 13 times 180 and then divide it by 6. Okay? If you have your calculator, this is very easy to do, and you get a nice number. You're going to get 390 degrees. Don't forget the units on your answer. Let's try negative 5 pi over 8. Again, we're trying to convert to degrees, so we multiply by 180 degrees over pi radians. So this is negative 5 times 180 degrees divided by 8. You want to reduce this as far as you can. You want a nice reasonable number, but in this case, if you divide it on your calculator, it's exactly equal to negative 112.5 degrees. In our last example, the angle is 2.4 radians. And notice that it doesn't have a pi in it, and that's because just because it's in radians doesn't mean there will be a pi in the angle. The procedure is the same. Multiply by 180 degrees over pi. Again, you want your answer to be in degrees, so be careful on this one that you don't get confused without the pi in there. And here you'll have to use your calculator. Multiply 2.4 times 180 degrees, divide by pi, and then round off to 1 decimal place or as required. It's about 137.5 degrees. Now, you've learned a lot of things in this video about drawing angles in standard position. You've learned about radian measure, and you've learned about converting between the two. You need to practice finding and drawing angles in standard position, practice finding coterminal angles, and while it's important to be able to convert your degrees in radians, don't use that as a crutch and learn to think in radians. It will help you throughout the remainder of your trigonometry course. In this video, we look at some applications of radian measure. We'll start with the area of a sector of a circle. So a sector of a circle is like a pie piece where the point is at the center of the circle, and the two sides here are both radii. We're going to start by looking at the fraction of the circle represented by that sector. We could calculate this two different ways. If we knew the area of the sector, we can write that over the area of the entire circle. And that's going to tell us the fraction of the circle that the sector represents. We could do this another way. We could look at angles. So we're going to call this central angle of the sector theta. And if we look at the angle that would be if we went all the way around the circle, then that's 1 complete revolution, or 2 pi radians. Okay? So either way we calculate the fraction of the circle present, it's the same fraction of the circle, so these two ratios are equal. Okay? Well, we know a little bit more than what I've written. The area of this sector is what we'd like to find. Let's just call that A. The area of the entire circle. We can calculate that using an old formula from geometry. It's pi times the radius squared. Our radius is r. The central angle theta, and then 2 pi. Now, one thing I should point out is it's pretty important theta is in radians, since I've used 2 pi radians to represent the entire circle, or all the way around it. Okay, so let's solve for A, the area of the sector. Multiply both sides by pi r squared. We can divide out those pi's and then sort of rearrange what's left. The area of the sector is 1/2 the radius squared times theta, with theta in radians. Now let's practice using this formula. In this example, we're asked to find the area of a sector of a circle where the central angle is 40 degrees and the radius is 5 centimeters. So we've just found this great formula. The area is 1/2 r squared theta, but theta needs to be in radians. So that's our first problem, okay? So whenever we're using a formula, we should always write it down before we begin, and then we can substitute in there. But as we've discussed, this needs to be in radians. So we're going to take our 40 degrees and to the side here, convert that to radians. How do we convert? Pi radians is 180 degrees. So we're going to multiply this by pi over 180 degrees. And for now, we're just going to reduce that to lowest terms and keep it as an exact value so I can go a little bit further. That's really 2 pi over 9. Okay? Now we're ready to substitute. The area is 1/2 the radius, which is 5 squared, times 2 pi over 9. Now I should stop here because my instructions didn't really tell me how to leave my answer. So we're going to start by giving an exact answer that's left in terms of pi, and then we'll approximate it if we need to later. Okay? All right, so what can we do? Well, 1/2 times 2 is 1. So I can write this as 25 pi over 9. Okay? What kind of units would the area of the sector have? The radius is given in centimeters, so area should be in square centimeters. Okay? This is an exact version of our answer. Sometimes you're asked to approximate your answer to 1 or 2 decimal places. At that point, you would take your calculator out and multiply and divide on your calculator to get an approximation. Let's do that real quick. So this is approximately 8.73. So we're going to use 2 decimal places here. Centimeters squared. And the number of decimal places will always be told to you in your homework or in any problem that you're working. Here's a second example of the area of a sector of a circle. Find the radius of a sector of a circle given the central angle is 3/5 radians and the area of the sector is 600 square feet. Round our answer to 1 decimal place. Okay, so we know we can use that formula. Area is 1/2 r squared theta for a sector of a circle. Theta needs to be in radians, so let's check that first. Great, this time we have our angle given in radians. But what's the difference in this problem? I'm not looking for the area. I already know that's 600 square feet. I know the central angle, but I need to find the radius. So the algebra in solving this one's a little bit more involved. Okay, so let's start by substituting what we know. The area of the sector is 600. The radius is what I'd like to try to find, and theta is 3/5 radians. Okay, I'm going to simplify the right-hand side by multiplying those fractions. That's 3/10 times r squared. And I need to get that r squared by itself. So let's multiply both sides by the reciprocal of 3/10. That would be 10/3. So we have 10/3 times 600 equals 10/3 times 3/10 is 1. So this is just r squared. Okay. 10 times 600 is 6,000. Divide that by 3, so we have 2,000 equals r squared. Now that's not a perfect square, so I'm going to grab my calculator so we can approximate it. R is going to be the square root of 2,000. Certainly going to be a positive number because it's the radius of our circle. The square root of 2,000 is about 44.7 rounded to 1 decimal place. What would the units be for our radius? Well, the area of the sector was in square feet, so our radius should be in feet. Next, we're going to look at arc length. This is the length of an arc or a portion of a circle. Okay, so I've drawn a circle with radius r. This is the center point. I have a central angle, theta again, and the arc is labeled S, and it's this portion of the circle intercepted by the central angle. I'd like to be able to calculate the length of that arc, knowing just the central angle and the radius. I'd like to look again at fraction of the circle represented by, in this case, the arc. Okay. So we're going to do the arc length over the circumference or distance around the entire circle. And then we're going to look again at the angles. So the central angle for this arc is theta. And an angle that starts here and goes all the way around the circle is 2 pi radians. So again, we're going to have that stipulation that theta has to be in radians. Okay. Now we've written the fraction of the circle present 2 ways, but they're the same fraction of the same circle, so they have to be equal. Okay. Arc length, we're going to use the letter S. Circumference of a circle, do you remember that formula? 2 pi times the radius of the circle. Okay, let's solve for S. Multiply both sides by 2 pi r. Notice that the 2 pi's divide out for us, and we're left with a very simple formula. S equals r theta, theta in radians. Let's practice using our arc length formula. We'd like to find the exact length of an arc of a circle with radius 10 feet that's intercepted by a central angle 330 degrees. So we have this nice formula, S equals r theta, but theta has to be in radians. We're given the central angle 330 degrees, so before we do anything else, we need to go ahead and change this to radians. There are pi radians in 180 degrees, so we're going to multiply by pi over 180. So this one just is 33 pi over 18. Oh wait, I can go further. Those both have a common factor of 3. So this is really 11 pi over 6, okay? Now we substitute. The radius is 10 feet. Theta is 11 pi over 6. Think of this as 10 over 1 and reduce your fractions. So I'm going to just go ahead and multiply. 10 times 11 is 110 pi over 6. And then reduce that. What kind of units would arc length have? Well, it's just a length. So whatever the length unit is used for the radius, we'll use for our arc length. So 10 feet. We wanted an exact value, so we want to leave it in terms of pi and an improper fraction. Here's another example that uses our arc length formula. Find the central angle of a circle with radius 30 inches that intercepts an arc of length 10 inches. Okay, so we can use our arc length formula, S equals R theta. And in this case, we're looking for the central angle. Okay, so that's what we don't know. Our radius is 30 inches, and the arc length is 10 inches. So an arc of length 10 inches, this is the S in our formula. R is 30. Okay. If we divide both sides by 30, we'll have theta by itself already. So theta is 10 over 30, or 1/3. 1/3 what? What are the units for our angle theta? Right. So theta, in order to use this formula, has to be in radians. So when we solve this, we're finding our angle theta in radians. If a particular problem asks you for that answer in degrees, then you know how to convert from radians to degrees, and you can do that at that time. So you need to learn both of these formulas for area of a sector and for arc length. Don't forget that your angle theta has to be in radians each time that you use them. And then practice these examples until you're comfortable with these skills.
Hi, let's take a look at an interesting property of right triangles. Suppose we draw a right triangle and we label the sides A, B, and C. The side C, which is the side opposite the right angle, is called the hypotenuse. That's Hypotenuse. Now, in terms of the angle theta, which I will select this angle and call it theta, then the side B is the side opposite the angle theta, and the side A is the side next to or adjacent the angle theta. Now let's take a look at the ratios of the sides of the right triangle. Let's pick, for example, the ratio of the length of side B to the length of side A. We could write that as B divided by A. Now, here's the interesting property. If we extend this side and we extend this side, even if it goes through the words, and then we close out the right triangle, we see something interesting. We can call this side right here B prime, and then we call this new side here A prime. And here's the part that's really interesting. The ratio of B prime to A prime is the same as the ratio of B to A. So what that means is that the ratios of the sides of the triangle depend only on the specific angle theta that is selected, as long as you're working in a right triangle. So in trigonometry, the ratios of all the pairs of sides are given special names. There are 6 of them. Let's go through them and define them in terms of the sides of the triangle. The first one is called the sine, and it's spelled S-I-N-E. It's abbreviated S-I-N. And the way it works is this. The sine of theta is the value given to the ratio of the opposite side divided by the hypotenuse. And we'll just abbreviate here, opposite divided by hypotenuse. Okay? The next function we're going to look at is the cosine function. It is abbreviated COS. And so the cosine of theta is the ratio of the adjacent side to the hypotenuse. The next one is called the tangent. It is abbreviated TAN. And the tangent of theta is the ratio of the opposite side to the adjacent side. All right, that's half of them. There are 3 more. The next one is called the cosecant, C-O-S-E-C-A-N-T, abbreviated CSC, and the cosecant of theta is the ratio of the hypotenuse to the opposite side. Okay. The next one is called the secant. It is abbreviated SEC, and the secant of theta is the ratio of the adjacent side to the ratio of the hypotenuse to the adjacent side. And then the last one is the cotangent, abbreviated COT, and it is the ratio of the adjacent side to the opposite side. These 6 ratios and their associated names in terms of angle theta are called the right triangle definitions of the trig functions of theta. You need to study these carefully. You need to practice writing them over and over again till you're absolutely comfortable with them. Now let's take a look at an example of how this is used. Use the definitions to find the trig functions for the given triangle. All right, so what do we have? We have a right triangle, we have a designated angle theta, and we know that the side opposite theta is 2 units long, and the side adjacent to theta is 5 units long. So what's missing? Well, of course, what's missing is the hypotenuse, this side right here. We know this is a right triangle, so let's find the hypotenuse. We want to know the length of side C. All right, now what's the relationship? Think about it. What's the Pythagorean theorem say about the relationship of the 3 sides? Right. It is C squared equals A squared plus B squared. We're looking for side C, so we're going to write C squared is, A is 5, so that's 5 squared, and B is 2, so that's 2 squared. So C squared is 25 plus 4, which is 29. Now, this is an algebraic expression, and so when you take the square root of both sides, algebraically unrelated to geometry, you would get plus or minus the square root of 29. But because this is the length of a side of a triangle, there's a geometric restriction here, which says, of course, the side of a triangle can't be negative. And so in our case, C is the square root of 29. By the way, you will do this process many times in trigonometry. You may want to start trying to think of doing it mentally. And here's what you would do. You're looking for the hypotenuse. You square this side, 25, this side, 4, add them together, 29, square root of 29. And so get used to practicing this mentally. It'll save you a lot of time. All right, so back to the problem. We need to use the definitions. Do you remember them? If not, get them out in front of you and then practice so in the future you will remember the 6 trig functions. Okay, here we go. We start with sine. Okay, the sine of theta is, and say it to yourself, it is the opposite over the hypotenuse. So that's 2 over the square root of 29. Okay, now we're going to stop for a second. Unless you are specifically told to do so, there is no reason why you have to rationalize this denominator. It is perfectly acceptable to leave this unless you have instructions that tell you otherwise. Okay, the cosine of theta is adjacent over hypotenuse. So that's 5 over the square root of 29. And then the tangent of theta. Okay, say it to yourself. What is it? It is the opposite over the adjacent. So it's 2 over 5. All right, next 3. Cosecant of theta is the hypotenuse over the opposite. Square root of 29 over 2. Be careful when you write this here. The 29 is under the radical. The division sign and the 2 is not. Okay, next one is secant of theta. And the secant of theta is the hypotenuse over the adjacent, correct. So it's the square root of 29 all over 5. And the last one is cotangent. And the cotangent of theta is equal to the adjacent over the opposite. And so it is 5 over 2. Okay, this satisfies the directions, but let's look at what we have here. These are the 6 trig functions of theta for this triangle. We calculated these using the definitions, but you've probably noticed at this point that there's a certain relationship between the 6 of these. So the next thing we're going to do is we're going to take a look at a little bit faster way to get some of these by using the relationships between them. All right, I have here on the board the definitions, the right triangle definitions of the 6 trig functions. What we want to do is look at the relationships. We're trying to see how of these fit together and how one is related to the other. Okay, well, first of all, I noticed that sine divided by cosine, well, what would it be? It would be this expression divided by this one. And if you simplified it, hypotenuse and hypotenuse would cancel, and you'd end up with opposite over adjacent, which is tangent. Okay, so we notice that relationship. So we say that the sine of theta divided by the cosine of theta is equal to the tangent of theta. All right, now let's look at these. What is the relationship between sine, cosine, and cotangent? Okay, and obviously there are lots of relationships, but there's some that seem to be used more often than others, so those are the ones we're going to point out here. Okay, what happens if you divide cosine by sine? Well, again, hypotenuse cancels, but you get adjacent over opposite, which is cotangent. So we're going to write down this one. Cosine of theta divided by sine of theta equals cotangent of theta. All right, these two in particular are what are called the quotient identities. Okay, and as I said, there are others, but these are the most used. Okay, now let's take a look at the reciprocal identities. Okay, well, sine is opposite over hypotenuse. Cosecant is hypotenuse over opposite. So what that means is that cosecant of theta is equal to 1 over the sine. And for that matter, the sine of theta is equal to 1 over the cosecant of theta. But once you learn the identity one way, of course, you can simplify it to get the other one. Okay, what else do we see? Well, we see that the secant of theta is equal to 1 over what? Cosine. And then what about the cotangent? The cotangent of theta is 1 over the tangent of theta. And these very descriptively are called reciprocal reciprocal identities, because that describes the relationship. Okay, the next group of identities take a little bit more thought, but not that much. What happens if you take the sine and you square it and the cosine and you square it? Okay, well, it's not quite as obvious from these definitions, but if you're curious about where this comes from, you can go back to a previous example that we did and actually take those values we did with the triangle that had the 2 and the 5 and the square root of 29, and you can square the values and see what happens, and I'll show you the result. The result is that if you take the sine and you square it, so the sine of theta squared, and you add it to the cosine squared of theta, you will get 1. Notice that this is really the same expression as the sine of theta squared. It doesn't mean anything strange like square a number and multiply it by theta. This is all one term raised to the second power, but this is how it's written. Okay, the next relationship that follows this pattern is that if you square the tangent of theta and you add 1, you will get the value of the secant squared of theta. And the third one is that if you take the cotangent of theta and square it and add 1, you will get the cosecant squared of theta. And these are called the Pythagorean identities. Together, this group this whole group together, these are called the fundamental identities. You need to practice these. You need to be very familiar with them. You need to be able to write them down. You need to be able to recall them with barely any effort whatsoever. Now, let's take a look at how this can be used. Example 2. Use identities to find the exact value of, and we have 2 expressions. Now down here at the bottom of the board, I have the fundamental identities that we developed in the last segment. I'm going to just leave them here so that we can refer to them. Okay, so let's see what we have. We have the tangent of 75 minus, and then we have the sine of 75 degrees divided by the cosine of 75 degrees. Okay, so what's the identity that we can use here to simplify this? Well, sine of theta divided by cosine of theta is tangent of theta. And since these angles are the same, both 75 degrees, we can rewrite this expression by copying over the first term, making no changes, and then replacing the second expression with the tangent of 75. And at this point, it's pretty obvious that the exact value is 0. All right, let's look at the second one. As soon as you see the sine squared, pi over 5, and then secant squared of pi over 5, where are you going to go? Sure, you're going to go to this expression here. Okay, now we have sine squared and secant squared, so that is a possibility of the first one or the second one. Well, let's see which one has the most promise. Well, we know that secant is related to what? Look around. Secant is related to cosine, they're reciprocals. And if I can change a secant expression to being defined in terms of cosine, then I should be able to use this identity second. All right, so first thing I'm going to do is I'm going to copy the first term. And then I'm going to rewrite the secant squared pi over 5. Let's see, secant and cosine are reciprocals. So if I have 1 over the secant squared of an angle, I should be able to write it as the cosine squared of the same angle. Now this is actually the reverse of the identity that I have written here. I'm actually using the cosine of theta is 1 over the secant of theta. But that's fine. Once you know this one, you can get the other one. And then what do I have? I have sine squared of an angle plus cosine squared of an angle is 1. All right, let's look at another example of how we use these identities. Example 3. Given that the sine of theta is 1/4 and that theta is an acute angle, find the exact value of the remaining 5 trig functions. All right, so let's take a look at what we have. So we have a right triangle. We know that because we're using trig functions, and of course they are trig functions of right triangles. So we have a right triangle. We just draw a little bitty one right here, just enough to label the sides. Here's angle theta, and the sine is 1 divided by 4. Think about the definition again. So that means 1. So that means this side is 1, and the hypotenuse is 4. So what's missing is this side. Now remember how I told you to learn how to do this mentally? Let's see if we can find this side mentally. It would be c squared equals a squared plus b squared. So what that means is this side squared is that one squared minus that one squared. So what do we get? We get 16 minus 1, which is 15, which means this side is the square root of 15 units. 16 minus 1, and then square root of both sides. Okay, so what we have is opposite, adjacent, and hypotenuse. But we have all of this. So we start. The sine of theta is given. Notice how every time I do this, I write 3 down, 3 more down in the same order. It helps for you to remember these things if you are very orderly and organized about how you do this. Okay, now, the cosine of theta. It is going to be adjacent over hypotenuse. Now, use the identities. What is tangent? Tangent is cosine divided by sine. And the 4's will cancel, and what you get is 1 over the square root of 15. Oops, let's look at that. Tangent, I think I said cosine over sine. Ooh, no. Tangent is sine over cosine. All right, so the tangent of theta, let's look at it again. It's sine divided by cosine. You do have to be careful when you do this because, of course, it's the same words over and over again. So it would be 1/4 divided by 15/4. The 4's cancel, and so what you do is write 1 over the square root of 15. Okay, now basically at this point you've got all of them because the next 3 are reciprocals of each of these 3. So as long as you are careful with what you write, the cosecant of theta would be the reciprocal of 1/4, which is 4. The secant of theta is the reciprocal of the cosine, and the cotangent of theta is the reciprocal of the tangent. All right, now before you stop, you go back and you check all of this. This was given. Cosine is this over this. Tangent is that divided by that from this identity. Cosecant is the reciprocal of this one. Secant, reciprocal of this one. Cotangent, reciprocal of this one, and you've got all 6. Let's look at another property of right triangles. Let's discuss the relationship of cofunctions of complementary angles. All right, from geometry, you may remember that complementary angles are angles that have a sum of, do you remember? Yes, 90 degrees or pi over 2. Okay, so let's remember that the word complementary means that 2 angles have the sum of 90 degrees or pi over 2. All right, so in this right triangle, we have the sides labeled A, B, C is the hypotenuse. This is the angle theta, right angle. So the question is, what is this angle in terms of theta? Well, I gave it away a little bit when I talked about complementary angles because if you remember, the sum of all 3 angles of a triangle is 180 degrees. So if it's a right triangle, then that means the sum of these 2 angles is, yes, 90 degrees, which means these are complementary angles. So what that means is that I can label this angle right here, and I'm going to bring it out to here. I'm going to label that angle as what's left. The sum is 90, so I could say theta plus this angle is 90. So what's left for this one is 90 degrees minus what was used here, or I could write it as pi over 2 minus theta. Okay, now you have to get used to this notation so that when you see it, you can spot it. So if this angle is theta, then the other acute angle in the right triangle could be written as 90 degrees minus theta, or it could be written as pi over 2 minus theta. All right, now let's look at co-functions of these complementary angles. All right, let's start with theta. Okay, with theta, let's just take the first one. So we'll say the sine of theta is. Okay, now remember the definition. The sine of theta is the opposite over the hypotenuse. So that's the length of side B divided by the length of side C. All right, now what is the co-function for sine? Think about the word co. Okay, sine, the co-function is the cosine. What is the value of the cosine? But we're not going to take the cosine of theta. We're going to look at the co-function of the complementary angle, which is this one. Now I can write it in either way. I'm going to choose to write it as pi over 2 minus theta. But I could have put 90 degrees minus theta. And so what is the cosine of this angle? All right, now think. Cosine is adjacent over hypotenuse. I'm using this angle, so this is the adjacent side. See, this is the opposite side, this is the adjacent side. So the cosine of this angle is B over C. Okay, well, as soon as I get to this point, what do you realize? You realize that co-functions of complementary angles are equal. Okay, so what we have is this. We have that the sine of theta is equal to the co-function of the complementary angle. Now, if we had all day, we could go through all of the other trig functions, but I think by this process you can see that I could write a similar situation for, let's say, the tangent of theta. And I could write this as equal to the cotangent of the complementary angle. And I could continue along with secant and cosecant. So I could write that the secant of theta is the cosecant of the complementary angle. All right, these and the rest of the relationships show you that co-functions of complementary angles are equal. Let's take a look at an example of how the complementary angle theorem can be used to simplify an expression. Okay, now you need to remember the fundamental identities, and I have some of the co-function of complementary angles expressions still listed down here, so we can refer to this. Okay, A says the cosine of 40 degrees divided by the sine of 50 degrees. Okay, well, it should jump out at you that the sum of 40 and 50 is 90, and so these are complementary angles. All right, so what that means is we can rewrite this expression. Let's go with the numerator. So the cosine of 40 degrees is equal to the cofunction of the complementary angle. And that's because if this angle is theta, then this angle is 90 degrees minus theta. And then we copy over the denominator, and immediately we see that what we have here is equal to 1. All right, let's look at B. 1 plus the tangent squared of 5 degrees minus the cosecant squared of 85 degrees. Okay, what hits you first? Well, maybe it's the fact that 5 degrees and 85 degrees are complementary angles. So we know somewhere we're going to use one of these. But we have tangent and cosecant, and none of this is going to be direct. So what we're going to have to do is find an identity, rewrite some of this, then use one of these parts of this, one of these complementary angle expressions. Okay, there are a couple of ways you can go here. I would think that the most efficient approach would be to recognize right away that this expression can be rewritten as what? Now think about the Pythagorean identity. Tangent squared of an angle plus 1 is equal to what? Okay, go through them. You should remember that it is secant squared of this angle, which is 5 degrees. Okay, then now I have minus cosecant squared of 85 degrees. Well, what can I do now? How can I write, say, this one in terms of 5 degrees? Well, this is cosecant. I could change either one of them. Actually, I just chose to do this one. I could rewrite this as the secant squared of 5 degrees, and then I know I've got it here because I've got the same two expressions. Subtract, and I get 0. All right, let's take a look at another example. This time, our angles are given in radian measure. C, we want to find the exact value of the sine of 5 pi over 12 divided by the cosine of pi over 12. Well, 5 pi over 12 and pi over 12 are not special angles, so we're not going to be able to find the exact value exactly as the expression is written. So let's look at the two angles. So I'm going to walk over here and I'm going to examine 5 pi over 12 and pi over 12. What if I added the two angles? Well, I would get 6 pi over 12, which is pi over 2. So now, what do we know about these two angles? They are complementary angles because the sum is pi over 2. Well, what do we know about complementary angles? We know that cofunctions of complementary angles are equal. So let's look. Here are some of the cofunction identities. We can rewrite the sine of 5 pi over 12 as the cosine of pi over 2 minus 5 pi over 12. Okay, and then I'll just copy the denominator over. Okay, and because of what we did over here, we see that pi over 2 minus 5 pi over 12 is the cosine of pi over 12. The denominator is the cosine of pi over 12. And so the exact value of this expression is 1. D. We want to find the exact value of the tangent of pi over 6 minus the cotangent of pi over 3. So once again, let's look at the two angles. Pi over 6 plus pi over 3. Well, we get a common denominator, so we write this as pi over 6, copying it over. We write this as 2 pi over 6. We add these, we get 3 pi over 6. We reduce, and we get pi over 2. So what have we found out? We found out here that pi over 6 and pi over 3 are complementary angles because their sum is pi over 2. So let's rewrite the tangent of pi over 6 using this second identity. It would be the cotangent of pi over 2 minus pi over 6. And then I copy this part over. Now, this, according to what we saw here can be rewritten as the cotangent of pi over 3. And so what do we have here? 0. Okay, now let's move on to another example. Example 5. Given the cosecant of theta is 6, find the exact value of these 4 expressions. Okay, now what you want to do here is use the most efficient method. So we have the definitions, we have the reciprocal, Pythagorean, and quotient identities, and then we have the cofunction of complementary angles relationships. So we go for what's most efficient. Well, let's see. The cosecant and the sine are related. They are reciprocals. This 6 is a whole number. It has a denominator of 1. The reciprocal of that would be 1/6. So the sine of theta is 1/6. All right, cotangent squared of theta. What do we know about cotangent squared that has a direct relationship to cosecant? Okay, well, we know this identity. We know that the cotangent squared of theta plus 1 is the cosecant squared of theta. We want to solve for cotangent squared, and that would be cosecant squared of theta minus 1. All right, well, we've just about got it, because cosecant squared would be 6 squared minus 1, and so that would be 35. All right, what about this one? Right away, you should see that this angle in these parentheses, this angle is the complement of the angle theta. So I can rewrite this expression. The cofunction of secant would be cosecant, and then the complement of this angle is 90 degrees minus theta. The complement of this angle is theta. And so what's the cosecant of theta? Given as 6. All right, part D, secant squared of theta. Okay, well, it's certainly not going to have anything to do with cofunctions of complementary angles. And in terms of identities, there is no identity that directly relates secant or secant squared with cosecant. So I think at this point, the most efficient thing to do is to draw a triangle, label the sides, and then just read directly off of the triangle. So let's draw a triangle. It doesn't have to all be perfect here, but just enough to get the idea. This is the cosecant, so this is going to be the hypotenuse over the opposite, or you can read from the sign, opposite over hypotenuse. So this is 6, and this is 1. The missing side is 36, minus 1 is 35, and then we take the square root. Okay, so there are the 3 sides. Now, the secant is, what to think about what that is. It's going to be the hypotenuse over the adjacent. The way I actually remember this is I think of the fact that it's the reciprocal of the cosine. Cosine is adjacent over hypotenuse, and then I take the reciprocal. Okay, so what do I have here? And we must not forget that it is squared. So let's set up for that before we read. And we want hypotenuse, which is 6, over adjacent, which is square root of 35. And we square that, so we get 36 over 35. So in summary, how do you find the exact values? You use everything you know about this. You use the right triangle definitions of the trig functions when appropriate. You use the complementary angle theorem when appropriate. And you also use identities when that's the most efficient method. You need to study all of these relationships and master them until you are perfectly comfortable using them. Computing trig functions of acute angles. Let's first talk about 3 acute angles. We call these special angles. Let's look at a 30-degree angle, which is pi over 6, a 45-degree angle, pi over 4, and then a 60-degree angle, pi over 3. And let's talk about finding the trig functions of these angles. Let's take 45 degrees first. Let's draw a triangle, and we will choose this triangle to be a right triangle, but we want it to be written so that it is an isosceles triangle where these two sides have the same length. Now, it really doesn't matter what the length is of these two sides as long as they are the same. Let's try to make this look a little more like they're the same. So for convenience sake, I will just say that the length of each side is 1. So what is the hypotenuse? All right, let's see if we know how to do this. We're looking for C. So it's this side squared plus this side squared. Add them together and then take the square root. So it's going to be 1 squared plus 1 squared is 1 plus 1, which is 2. So this side is the square root of 2. Well, let's see. If this is an isosceles triangle, then that means that this angle right here is 45 degrees. And of course, that was by design because I want to study the trig functions of a 45-degree angle. So let's see what we have. Okay, well, we know that the sine, and of course this is pi over 4, and you want to think in radians as well as degrees. So we say that the sine of 45 degrees is the opposite over hypotenuse. And again, there is no need to rationalize unless you are specifically told to do so. The cosine of 45 degrees is adjacent over hypotenuse. And the tangent of 45 degrees is 1 over 1, which is 1. All right, these are the first 3 trig functions. You can get the next 3 by taking the reciprocal of each one of these. So we will just leave that to be done when we need it. Now let's look at a 30-degree angle and a 60-degree angle at the same time. Okay, so we have a 30-degree angle, pi over 6, and we're going to also look at a 60-degree angle. And how are we going to do that? Well, we're going to draw an equilateral triangle, or some approximation of an equilateral triangle. Now we have to be creative here. We know that if it's an equilateral triangle, all 3 angles are 60 degrees. I want to represent 60 and 30 and read from there. So what I'm going to do is, okay, I know this is 60 degrees. I'm going to drop a perpendicular which bisects this side. That means that this angle is 30 degrees. And what I'll do is I'll just say that the length of this side is 2, making the length of this half of the same length 1. It's very convenient. You, of course, could use any numbers, but whatever you do, the ratio is that this will be twice that side. Okay, what is the length of this side? Okay, it's going to be 2 squared, which is 4, minus 1 squared, so that's 4 minus 1 is 3. So the length of this side will be the square root of 3. Reading from the triangle. All right, let's do 30 first, which means I'm going to read this triangle. This angle. So this side is opposite, this side is adjacent. Okay, so I'm going to do the sine of 30, and then I'm going to read the cosine of 30, and then the tangent of 30. Okay, all right. The sine of 30 is opposite over hypotenuse. The cosine of 30 is adjacent over hypotenuse. And the tangent of 30 is, and you can either read it from the triangle, or we've done enough of this now that we know that it's going to be 1 over the square root of 3, because we can use the identity, the reciprocal identity, that the tangent is the sine over the cosine. Okay, we can get the other 3 using the reciprocal properties. All right, now let's read the trig functions of the 60-degree angle. So we want the sine of 60, or pi over 3. We want the cosine of 60 and the tangent of 60. Okay, the sine is going to be opposite over hypotenuse. And then at this point, you might start to realize that cofunctions of complementary angles are equal. It means that the cosine of 30 equals the sine of 60, and the sine of 30 degrees is the cosine of 60 degrees. We don't necessarily have to read all of this. And then the tangent of 30 is going to be the opposite over the adjacent, which is the square root of 3, or the reciprocal of, well, let's not, we're not going to have cotangent here, so we're not going to write all those down. You can figure those out using the reciprocal. Okay, so what do we have here? We have some things that would be very convenient to memorize. So what we want to do is we want to make this little table. Okay, and you want the table, and I'm going to just write it in right here. You want the sine, the cosine, and the tangent. And this needs to go in here of 30 degrees, 45 degrees, and 60 degrees. And this is something you want to write down over and over and over and over again until you are just totally comfortable with it. Okay, so what do we have? We have the sine of 30. Okay, now that's this batch right here. Okay, so we have the sine of 30 is 1/2. The cosine of 30 is the square root of 3 over 2. And the tangent of 30 is 1 over the square root of 3. Okay, next column would be these. Sine and cosine are the same. You see how easy this is to memorize? You just get comfortable with it. And then the tangent of 45 is 1. And then we have this last batch. And so we have the sine of 60, which of course is the cosine of 30. So these are easy, they're just switched, and then this one is the reciprocal. This right here is so important. You will use it over and over and over again. Let's take a look at some examples where we use this information. Example 1. Find the exact value of each expression. Notice that what we have here are all trig functions of acute angles, but not only that, all of these acute angles are special angles. Below I have the table that we generated by drawing the triangles for 45, 30, and 60 degrees and finding the trig functions from there. You can of course use the triangles or you can use this table. All right, so let's see what we have. The sine of 45 degrees. Okay, the sine of 45 degrees is 1 over the square root of 2. We want to multiply that by the cosine of 30 degrees. The cosine of 30 degrees is the square root of 3 over 2. Now, what we're really doing here is practicing using this information. So we're going to multiply here, and we will get the square root of 3 over 2 square root of 2. Let me point out right here to you something about rationalizing. The sine and the cosine, in particular, say of 45 degrees, are 1 over the square root of 2. You don't have to rationalize, but if you chose to do so, you would multiply this expression by the square root of 2 over the square root of 2, which would then simplify, and you'd get the square root of 2 over 2. What you want to do is recognize that if you ever see this expression, it is equivalent to the 1 over the square root of 2 and also to this one. The same thing for this. This is actually equivalent to the square root of 3 over 3, and so you may see that at some point too. All right, let's go to B. The tangent of pi over 4. Okay, well the tangent of pi over 4 is 1, and the sine of pi over 3, which is 60 degrees, is the square root of 3 over 2. Now how can we simplify this? Well, we can get a common denominator, so we write 1 as 2 over 2, and then subtract the square root of 3 over 2. We can combine the terms in the numerator over the denominator. Okay, let's look at the third one. The tangent squared of pi over 6. Well, the tangent of pi over 6 is 1 over the square root of 3. And what we want to do is, from here, we want to square this. Then we want to add sine squared of pi over 4. So the sine of pi over 4 is 1 over the square root of 2. Don't forget to square it. And what do we get? This would be 1 over 3 plus 1 over 2. Common denominator, this would be 2/6, 3/6. Exact value, 5/6. All right, so what you need to do is memorize the trig functions of the 3 special angles and be able to use them quickly and efficiently. But what happens if your acute angle is not one of those 3 special angles? Then you need to use a calculator. Let's take an example of that and work out some exercises using the calculator. Example 2. Find the value correct to 2 decimal places. Notice that these are all trig functions of acute angles, but none of these are special angles. And so we're not going to be able to read off the triangle or the table that we've memorized. Instead, we're going to have to look up these values that are stored in our calculator. Okay, the big thing here is units. Degrees, radians, degrees, radians. Your calculator must be in the correct mode in order for you to get the correct answer. All right, so this is the sine of 48 degrees. Make sure your calculator is in degrees. The default is usually degrees, but you should always check that. Okay, so I'm in degrees, and now I want the sine of 48 degrees. Now, depending on what kind of calculator you have, you may have to enter this. If you have sort of an old-fashioned scientific calculator, you may have to put the angle in first and then the trig function. If you get one that has a display, which is what I would recommend, it's much easier to work with. You can depress the sine button, and then you can put in 48. It's already in degrees. Enter. And out comes the answer, and then I want to round correct to 2 decimal places. I get 0.743, and so when I round, I get approximately 0.74. All right, what unit is this? Radians. So clear your calculator and put it in radian mode. Okay, I'm bringing up radian mode. I am selecting it, and it now says radian mode. I want the cosine of pi over 12. So that's pi, and there's usually a key for pi, and then divided by 12. Enter, and I get 0.9659 and so forth. Rounded to 2 decimal places is going to be 0.96. Okay, now let's see. This was 9659, so you know when I round this, it should actually be 0.97. Be careful when you are rounding. Okay, let's clear the calculator, and let's go back to degree mode. Okay, so mode, degrees, enter. Okay, I'm in degrees, but This is the secant of 17 degrees, and if you look at the calculator, it has sine, cosine, and tangent. So how can I get the secant? Well, that's what we learned all those identities for. This is 1 over the cosine of 17 degrees. So let's enter that information. So it's 1 divided by the cosine of 17, I'm in degrees, enter, and I get 1.045, blah, blah, so this is going to have to be approximate because I'm rounding, and I'm going to get 1.0, and I have 45, so I'm going to round to 1.05. Okay, what about this one? Mode, correct. So clear the calculator, go back to radian mode, enter. The cosecant is 1 over, and I have to rewrite this in terms of either sine, cosine, or tangent. And what is it? Sine of pi over 5. So I'm in radians and I'm ready. It's 1 divided by the sine of pi divided by 5, and that is equal to 1.701. So that is going to be approximately 1.70, correct to 2 decimal places. And so this is the process you use to find the trig functions of acute angles when they are not special angles. You use your calculator. If you have a special angle, either 30, 60, or 45 degrees, you should know that information by heart. Practice it until you do.
In preparation for evaluating trigonometric functions of general angles, it is important to group the special angles into families. The first family we will look at is the quadrantal family. The first angle in the quadrantal family has a terminal side along the positive x-axis. This angle has a measure of 0 radians, also 0 degrees. The next quadrantal angle has a terminal side here, and it has a measure of pi over 2 radians, or 90 degrees. The next angle has a terminal side here, and it has a measure of pi radians, or 180 degrees. And then the fourth quadrantal angle we will look at has a terminal side here, and it has a measure of 3 pi over 2 radians, or 270 degrees. Now, there are infinitely many quadrantal angles, but they are all coterminal with one of these 4 angles. The next family we will look at is the pi over 3 family. All right, the first angle is pi over 3. So pi over 3 sits about here, has a terminal side in quadrant 1. It has a measure of pi over 3 radians, or 60 degrees. The next angle in the pi over 3 family, let's draw it right here, has a terminal side about here, and it has a measure of 2 pi over 3 radians, or 120 degrees. Now, watch what happens next. If we add another pi over 3, we would get an angle that has a terminal side on this axis. But we can see that that angle already belongs to the quadrantal family. So we skip 3 pi over 3, and we move to this angle, which has a measure of 4 pi over 3, which is equal to 240 degrees. Now, we add another pi over 3. This angle here has the measure of 5 pi over 3, or 300 degrees. And then we can check this, because if we add another pi over 3, we get right back to one rotation, which is 2 pi. So now we have the 4 major angles in the pi over 3 family, and then there of course are infinitely many others, but they are all coterminal with one of these 4. Okay? Next we look at the pi over 4 family. Okay, first angle, pi over 4. Or 45 degrees. Now if you add another pi over 4, you would get to 2 pi over 4. But when you reduce that, you get pi over 2. And once again, that angle is already a quadrantal angle. So now we have 1 pi over 4, 2 pi over 4. And so the next angle in this family would be 3 pi over 4, which is 135 degrees. Okay, now we add another pi over 4, and you see what's going to happen again. We get an angle that's coterminal with any angle on this axis, and of course, once again, that's here. So we add another pi over 4, and you see the routine. So we have pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, and now this is 5 pi over 4, which is 225 degrees, and that's this angle. And then the last one is going to be this one, which is 7 pi over 4, or 315 degrees. Once again, there are an infinite number of angles that are in the pi over 4 family, but they are all coterminal with one of these 4. Now we look at the pi over 6 family. Okay, first angle, pi over 6. So this is pi over 6, which is 30 degrees. Okay. Now, another pi over 6 would be 2 pi over 6, but that's pi over 3. And then we'd have 3 pi over 6, which is here, and then 4 pi over 6, which is here. And so the next angle we're actually going to identify as being part of this family is 5 pi over 6, which is 150 degrees. Okay, then we'd have 6 pi over 6, which we don't identify because, again, that's pi. Then this one is 7 pi over 6, which is 210 degrees. Then we'd have 8 pi over 6, 9 pi over 6, 10 pi over 6, and those are all already represented. And then the last one is 11 pi over 6. Let's make that a little bigger, which is 330 degrees. You need to practice drawing these angles and get used to identifying which of these special angles fit into which family. Let's take a look at identifying the angle family that a given angle belongs to. We will sketch the given angle. We will find theta c, the coterminal angle, which is the angle of least non-negative measure coterminal with the given angle. And then we will identify the special angle family. The first one we're going to look at is the given angle theta is 33 pi over 6. Hopefully the first thing you will notice about this is that 33 and 6 have a common factor of 3, and we need to simplify this fraction before we look at anything else. So we're going to divide the numerator and the denominator each by 3, and we will get 11 pi over 2. Okay, now we will sketch theta. Now let's look at what we have. Remember that one rotation in terms of pi over 2 would be 4 pi over 2. Okay, so what we're thinking is that 2 pi is 4 pi over 2. So to find theta c for 11 pi over 2, we'd have 4 pi over 2, 8 pi over 2, and then 9, 10, 11 pi over 2. You could do this algebraically by just repeatedly subtracting 4 pi over 2 from the given angle until you get an angle of least non-negative measure, which would be, in this case, 3 pi over 2. So that is theta c. Okay. Once we look at this, we realize that this is a special angle, and it belongs to the quadrantal family. And so when we identify the angle family, we would write the word quadrantal. Let's take a look at another example. So here we have theta equals negative 840 degrees. First, I'm going to draw this angle. Now, because it's a negative angle, I start here, go in this direction, and each rotation is going to be negative 360 degrees. So this would be negative 360, negative 720, and then another negative 120. So this part is negative 120 degrees, which means that this part would be positive 240 degrees. You can always check this algebraically by adding 360 degrees repeatedly to this angle until you get the angle of least positive measure, which is theta c. Okay, so here we have theta c is 240 degrees, and the angle family is pi over 3, or in this case we would say 60 degrees. In order to create the definitions of the trigonometric functions of general angles, we start by reviewing the right triangle definitions of trigonometric functions. So we have the sine of theta is opposite over hypotenuse, cosine of theta is adjacent over hypotenuse, and tangent of theta is opposite over adjacent. We know that the other three functions are reciprocals, each one of these. Notice here that theta is an acute angle. To extend the right triangle definitions of the trigonometric functions to include all general angles, that means angles with positive measure, negative measure, zero measure, and no limit in size, we take a look at a point on the terminal side of the angle. So here's theta, and I pick a point on the terminal side, and that point has coordinates xy, and I look at the length of this line segment. I choose to call it R, and looking at this right triangle, I can see that R is equal to the square root of x squared plus y squared. Now, using the right triangle definitions for theta, and let's move this label for theta over to here, much better, then I can see that the sine of theta would be opposite, but if you look at this as the coordinate, this is actually the y coordinate, and then of course this is the x coordinate. So let's go back. The sine of theta is opposite over hypotenuse. Okay, so the sine of theta is opposite over hypotenuse. And so what we use here are the coordinates of the point. All right, by the same process, I can see that the cosine of theta adjacent over hypotenuse would be x over r, and then the tangent of theta would be y over x, which is opposite over adjacent. All right, now let's take a look at an angle that has a terminal side that is not in quadrant 1. So let's try quadrant 2. So here's theta. Here is a point on the terminal side of theta. The length of this line segment, r, is, again, equal to the square root of x squared plus y squared. And we can see now that we can use this same representation, but this time using the coordinates of the points. And we can find the trig functions of the representations of the other three trig functions using reciprocals. So let's write this all down. So the sine of theta for any angle is y over r. The cosine is x over r. And the tangent of theta is y over x, where x and y are the coordinates on the point of the terminal side of theta. Notice here that x cannot equal 0. Now, the cosecant of theta, using the reciprocal identity, is r over y, where y does not equal 0. The secant of theta is r over x, where x does not equal 0. And finally, the cotangent of theta is x over y, where y does not equal 0. And so now we have the definition of the 6 trigonometric functions for general angles. Let's take a look at an example. The point P with coordinates 12, negative 10, this point lies on the terminal side of theta. We want to find the exact value of the 6 trigonometric functions of theta. And here are the definitions of the trigonometric functions for general angles. So the first thing we're going to do is we will plot the point 12, negative 10. So 12 is, we'll say, out here somewhere. Negative 10 is about here. So the point is about here. Then that means that theta has the terminal side that lies in quadrant 4, represented by this positive angle. In this situation, we know that the x coordinate is 12 and the y coordinate is negative 10. The piece we're missing is r. Okay, so we're going to find r. We know that r is the square root of x squared plus y squared. So r is the square root of 12 squared plus negative 10 squared. So r is the square root of 144 plus 100. So that's 244. Now, we must simplify this radical, which means we have to look to see if there is a factor here of 244 that is a perfect square. It's pretty obvious, I think, that 4 times 61 is 244. The square root of 4 is 2. And so this is what I'm going to use for r. Okay. Now all I have to do is fill in. So the sine of theta is y over r. And as soon as we look at this, we see that we have a common factor of 2. So we're going to simplify this expression and get 5 over the square root of 61. Then we have the cosine of theta is x over r. So that's 12 over 2 times the square root of 61, which is 6 over the square root of 61. And then the tangent of theta is y over x. So this is y over x. And when I reduce this, I get 5/6. So here's the sine, the cosine, and the tangent for theta. And now I can find the other 3 values by taking the reciprocals. So the cosecant of theta would be negative square root 61 over 5. The secant of theta would be square root of 61 over 6. And the cotangent of theta would be negative 6 over 5. And so now we have found the exact values of the 6 trigonometric functions of theta having a point on the terminal side 12, negative 10. Let's find the values of the trigonometric functions for quadrantal angles. Let's start with the first quadrantal angle. This would be angle with the terminal side on the positive x-axis. And what we will do is we will pick any point on this terminal side, and you can see that a point here would have a coordinate of x, and then the y coordinate would be 0. So this will be our point P. You can also see that the length of this line segment, which we usually call r, in this case is actually going to have the value of x. So from this, using our definitions, we can find the sine of 0, the cosine of 0, the tangent of 0, and then using the reciprocal property, we can find the other 3 values. So let's see. The sine of 0 from the definition is y over r. So it would be 0 over x. So the sine of 0 is 0. The cosine of 0 is x over r. And so that would be x over x, which is 1. Then the tangent of 0 would be, from the definition, y over x. Y is 0, x is x, and we get 0. Okay, what we can do now is find the other 3 using the reciprocal property. Well, that gets pretty interesting with 0. So let's take a look at the definition. The cosecant of 0 would be r over y, which is going to be x over 0. So what we see here is that the cosecant of 0 is undefined. Okay. The secant of 0 would be r over x, and that's x over x, which is 1, and that's no surprise because the reciprocal of 1 is 1. And then the cotangent of 0 is x over y, so that's x over 0, and we have the same situation here. And so the cotangent of 0 is undefined. Now what we can do is we can find the trig functions for pi over 2, pi, and 3 pi over 2 by the same method. Let's find the values of the trigonometric functions for pi. So here, theta is pi, or 180 degrees. A point on the terminal side of pi would have coordinates x, which is going to be a negative value, and then the y coordinate will be 0. Now, the length of this line segment is r, and r is a positive number. But when we identify the values of x, y, and r for this angle, we know that x is equal to x, y is equal to 0, but r has to be positive, and we know that x is negative, so in order to make this positive, we realize that r has to be the opposite of x. Now we use the definition. So the sine of pi is equal to y over r, which is 0. The cosine of pi is x over r, and the tangent of pi is y over x, which is 0. Okay, now let's get the other 3. The cosecant of pi is going to be r over y, and this is undefined. The secant of pi is r over x, and the cotangent of pi is x over y, so that's x over y, which is undefined. By continuing in a similar manner, we are able to find the values of the trigonometric functions for all of the quadrantal angles. Here they are in a table. Let's take a look at an example. Find the exact value of the tangent of negative 7 pi over 2 without a calculator. So, first of all, we have to find the terminal side of negative 7 pi over 2. We know that one rotation in this direction is negative 4 pi over 2, and then this would be negative 5, negative 6, negative 7 pi over 2. So we see that the terminal side of this angle lies on the positive y-axis. This is a quadrantal angle. We will pick a point on the terminal side here, and we will label this point 0, y. Okay? And now we will also look at the length of this line, which is also, we call it r, but in this case you can see that it is y. So I'm going to identify x is 0, y is actually the value y, and r is also y. Okay, I want to find the tangent of negative 7 pi over 2. And so I use the definition y over x, and I get y over 0, which we know is undefined. So I can't really find the exact value of this expression, but I can say that it is undefined. Let's find the signs, that's the S-I-G-N-S signs, of the trigonometric functions by quadrant. Well, since r is always positive, the sign, the SIGN sign, is dependent completely on the sine of x and the sine of y based on the point on the terminal side of the angle. So if we look at the 4 quadrants, 1, 2, 3, and 4. Let's think about the values of x and y. In this quadrant, x and y are both positive. If the angle has a terminal side in this quadrant, think about what you would get. Well, you would get a negative value for x, a positive value for y. If the angle has a terminal side in this quadrant, both x and y will be negative numbers, and here x will be a positive value and y will be negative. Let's take a look at each quadrant one at a time. Quadrant 1. In quadrant 1, x, y, and r are all positive, and therefore, for an angle that has a terminal side in quadrant 1, all of the trig functions will be positive. In quadrant 2, if an angle has a terminal side in quadrant 2, x will be a negative number, y will be a positive number, and r, as always, will be a positive number. So, the sine of an angle with a terminal side in quadrant 2 would be y over r, which in this case would be represented by a positive number over a positive number, which would yield a positive number. The cosine of an angle that has a terminal side in quadrant 2 would be represented by x over r, where x is a negative number and r is a positive number, and a negative number divided by a positive number would yield a negative number. Okay, the tangent of theta, where theta has a terminal side in quadrant 2, would be y over x, where y is represented by a positive number and x is represented by a negative number, and the result would produce a negative number. So what we see here is that if an angle has a terminal side in quadrant 2, the sign, the SIGN sign, would be for the sine function positive, for the cosine function negative, and the tangent function negative. So what that means is that the cosecant for an angle that has a terminal side in quadrant 2 would also be positive, because these are reciprocal functions, for the secant negative, and the cotangent negative. We can continue in a like manner for angles that have terminal sides in quadrant 3 and 4. After finding the signs of the trigonometric functions in the remaining quadrants, this is the result. We see that if an angle has a terminal side in quadrant 1, all 6 trig functions will have a positive value. If an angle has a terminal side in quadrant 2, we see that both the sine function and the cosecant function will be positive, and the other 4 functions will have a negative value. If an angle has a terminal side in quadrant 3, both the tangent and the cotangent will have positive values. The other 4 will have negative values. And then in quadrant 4, if an angle has a terminal side here, then the cosine and the secant will both be positive, and the other 4 trig functions will have negative values. Now let me show you how you will more often than not use this information. When evaluating the sine of theta, if theta has a terminal side in quadrant 1, then the sine of theta will be positive. If theta has a terminal side in quadrant 2, the sine will be positive. If theta has a terminal side in quadrant 3, the sine will not be positive, it will be negative. And the same thing if theta has a terminal side in quadrant 4, the sine of theta will be negative. If we're evaluating the cosine of theta, then if theta has a terminal side in quadrant 1, once again we know the cosine of theta will be positive. In quadrant 2, when the terminal side of theta lies here, the cosine will be negative. If the terminal side of theta lies in quadrant 3, the cosine will be negative. And if the terminal side of theta lies in quadrant 4, the cosine will be positive. And then we will look at the tangent function. Again, if the terminal side of theta lies in quadrant 1, the tangent of theta will be positive. If the terminal side of theta lies in quadrant 2, the tangent will be negative. If the terminal side of theta lies in quadrant 3, the tangent of theta will be positive. And if the terminal side of theta lies in quadrant 4, the tangent will be negative. These 3 diagrams will be particularly useful as you further your knowledge and study of trigonometry. Let's look at an example. If the tangent of theta is greater than 0, positive, and the sine of theta is less than 0, negative, then theta has a terminal side that lies in what quadrant? Well, let's take a look. If the tangent of theta is greater than 0, that means the tangent is positive. So we look here and we see that the tangent of theta would have a positive value if the terminal side of theta lies in quadrant 1 or quadrant 3. So this is true for these two quadrants. Now, the sine of theta is negative, means that the terminal side of theta lies in quadrant 3 or quadrant 4. And because we have here and, we're looking for the quadrant that applies in both cases, and we see that quadrant 3 is the only possible quadrant that the terminal side of theta could lie in that meets these two conditions. Let's look at another example. If the tangent of theta equals -3/7 and the cosecant of theta is positive, then find the sine of theta. Well, the first thing we have to do is determine where the terminal side of theta lies. And we will get that information from the fact that the tangent of theta is negative and the cosecant of theta is positive. So let's find the quadrants. The tangent is negative when theta has a terminal side in quadrant 2 or 4. The cosecant is positive, which means that the sine is positive because they're reciprocal functions. So the sine is positive if theta has a terminal side in quadrant 1 or quadrant 2. And the only quadrant here that these two conditions have in common is quadrant 2, so that is where the terminal side of theta lies. So let's draw theta and see what we can determine. So here's theta, and we know from what was given that we can find x, y, and r. Now, be careful here. In this quadrant, a point on the terminal side of theta will have a negative x value and a positive y value. So what that means here is that because the tangent is y over x, it means that the negative sign actually goes with the 7. So what I'm going to put is a 7 here and then 3 here. Next I have to find r. So r is the square root of x squared plus y squared. So r is 49 plus 9, which is the square root of 58. Now we check to see if we can simplify this radical, and we look for a factor of 58 that is a perfect square. Okay, we see that there aren't any, and so we use the square root of 58. Okay, and then the last thing we have to do is find the sine of theta. So the sine of theta is y over r, and in this case y is 3 and r is the square root of 58, and that is the sine of theta for these conditions. Let's take a look at determining reference angles. The reference angle, denoted by theta sub r, is the positive acute angle associated with a given angle theta. Now all angles except quadrantal angles have an associated reference angle. You can find this angle, this reference angle, because it is the angle between the nearest x-axis and the terminal side of theta c. And we put nearest in quotation marks because we really mean nearest half of the x-axis. So let's take a look at what this means. So if I have an angle, theta, and I find theta c, the coterminal angle, and that angle has a terminal side that lies in quadrant 1. Then the reference angle is equal to theta c. And that's the simplest case. All right, let's look at the situation where theta c has a terminal side that lies in quadrant 2. Okay, the reference angle is this angle because this is the nearest half of the x-axis. We find the measure of the reference angle by starting with pi, which would be the angle from here to here, and then we subtract theta c, and the remainder is then theta r. For the case where the terminal side of theta c lies in quadrant 3, so this is theta c, this angle, then this is the reference angle. Because again, it is the angle between the nearest half of the x-axis and the terminal side of theta c. So to find the reference angle in this case, we would take theta c and then we would subtract pi. And what is left would be the reference angle. The fourth case would be where the terminal side of theta c lies in quadrant 4, and this would be the reference angle, and we would find that angle by starting with 2 pi and subtracting theta c. And that is how we would find the reference angle in each of the 4 quadrants. Let's take a look at some examples of determining the reference angle. We want to find theta c, then we want to find the quadrant in which the terminal side of theta c lies, and then we will find the reference angle. So let's look at the first theta. We have negative 41 pi over 6. We have to find theta c. And so one thing to do is to realize that one rotation would be 12 pi over 6. And so if you think in multiples of 12, you can add to this fraction multiples of 12 until you get a positive number. So what I'm thinking here is I could add 12 pi over 6, or 24 pi over 6, or 36 pi over 6, or 48 pi over 6. And as soon as I get to 48, I realize that the theta c would be this angle plus 48 pi over 6, because that will give me a positive number. And so this would be 7 pi over 6. And that would be theta c. Now, I know that 7 pi over 6 has a terminal side in quadrant 3. So here's my theta c, terminal side in quadrant 3. And now I have to find the reference angle. Well, this is the reference angle. I can find it algebraically by taking the value of theta c and then subtracting pi. So that would be 7 pi over 6 minus pi, which would be 6 pi over 6. And so what I get is that the reference angle is pi over 6. As you practice doing exercises of this type, you will come to discover that if you have a special angle that's reduced to lowest terms, then the reference angle is going to be pi divided by whatever the denominator is, which in this case is pi over 6. Okay, let's look at this example. So I have theta is 24 pi over 9. What's the first thing you notice about this? Well, you should notice that both of these numbers are divisible by 3. So what I'm going to do is I'm going to rewrite this angle as 8 pi over 3 by dividing the numerator and the denominator each by 3. And now I'm going to find theta c. So one rotation in terms of pi over 3 would be 6 pi over 3. That's equal to 2 pi. So I'm going to subtract that out and get 2 pi over 3, and that's theta c. Okay? 2 pi over 3 has a terminal side in quadrant 2, and so the reference angle, and from what you learned on this example, you probably already know that the reference angle is pi over 3, but let's work it out. So here, theta r is pi minus theta c. So pi, and we want denominator of 3, so we're going to rewrite pi as 3 pi over 3 minus theta c. And we are not at all surprised to see that the reference angle is pi over 3. On the next example, the first thing you might notice is that the denominator is 10. So this is not going to be one of the special angles, but we will use the same procedure. So theta c is going to be 37 pi over 10, and then we will subtract 2 pi in the form of 20 pi over 10, and we will get 17 pi over 10, and that is theta c. Now we don't just know exactly where the terminal side of this lies like we do with special angles, so let's count. One rotation would be 20 pi over 10, so each quarter of a rotation would be 5 pi over 10. So this would be 5, 10, 15, and then all the way around would be 20, so somewhere in about here is 17 pi over 10. And so the reference angle is here, and we would find the value of it by writing 2 pi and then subtracting theta c. Now, since our denominator is 10, we're going to write 2 pi again as 20 pi over 10, and then we're going to subtract 17 pi over 10, and what we get is the reference angle is 3 pi over 10. And at this point, you realize that your reference angle is not always going to just be pi over the denominator, because in this case, it is not. let's take a look at an example where theta is measured in degrees. Same process. We look for a coterminal angle. We're going to subtract, in this case, 360 degrees. And when we subtract, we get 60 degrees, and that's theta c. Well, we know that 60 degrees has a terminal side in quadrant 1. And in this case, the reference angle is the coterminal angle, which is 60 degrees.
Before we can evaluate trigonometric functions of angles belonging to the pi over 6, pi over 4, or pi over 3 families, we need to make an observation. Notice here that all 4 of these angles are the angles that belong to the pi over 6 family of special angles. Notice that they all have the same reference angle, that being pi over 6. Notice that because the tangent is defined as y over x, we can label a point on the terminal side of pi over 6 as square root of 3, 1. By that same token, we can label points on the terminal sides of 5 pi over 6, 7 pi over 6, and 11 pi over 6, and from there we can find the trig functions, in particular the tangent, of those 3 angles. Now, what do we observe? We observe that the only thing that differs here is the plus or minus sign. So, in order to find the trigonometric functions of angles belonging to special angle families, all we really need to know is the reference angle, and then we need to know the quadrant that the terminal side of the angle lies in, because that will help us to determine whether the trig function is positive or negative. In order to evaluate trigonometric functions of angles belonging to the pi over 6, pi over 4, or pi over 3 families, you will need to use many of the things you have learned earlier in this section. First, we're going to find the cosine of 7 pi over 6. I will sketch 7 pi over 6. I will see that the terminal side of 7 pi over 6 lies in quadrant 3. I know that the cosine for an angle that has a terminal side in quadrant 3 will be a negative number. I know that the reference angle will be pi over 6. Therefore, the cosine of 7 pi over 6 is equal to negative cosine pi over 6. I know that the cosine of pi over 6 from either the special angle, so this is pi over 6, I know the cosine is adjacent over hypotenuse, square root of 3 over 2, or if you prefer to use the table, the cosine of pi over 6 is here, the square root of 3 over 2. So I substitute the square root of 3 over 2 here, and I get that the cosine of 7 pi over 6 is equal to negative square root of 3 over 2. Now let's find the cosecant of 2 pi over 3. Two pi over 3 has a terminal side that lies in quadrant 2. Now, the cosecant is going to have the same sign, S-I-G-N sign, as the sine function has in quadrant 2,
which is positive. The reference angle is pi over 3. And now we have to be careful because we are going to write the cosecant of 2 pi over 3 is equal to the cosecant of the reference angle, and that is equal to 1 over the sine of pi over 3. I'm going to go to the table and I'm going to read the sine of pi over 3 is the square root of 3 over 2. That goes in the denominator, and so what I have is 1 over the square root of 3 over 2, that's a 3. And so when I simplify this expression, I'm going to get 2 over the square root of 3. We now want to evaluate the cosine of negative 4 pi over 3. Negative 4 pi over 3, well, this would be negative 3 pi over 3. So negative 4 pi over 3 would have a terminal side that lies in quadrant 2. The cosine in quadrant 2 for an angle that has a terminal side in quadrant 2 is going to be a negative number. The reference angle will be pi over 3. Now the cosine of negative 4 pi over 3 is equal to the cosine of the reference angle, but I have to incorporate the negative here, so let's squeeze that in here and then put pi over 3. So I get negative, and then the cosine of pi over 3 is 1/2. Here are 2 more examples of evaluating trigonometric functions of angles belonging to one of these families. We want to find the tangent of 13 pi over 4. We want to sketch 13 pi over 4 and determine the quadrant that the terminal side of the angle lies in. We know that one rotation is 8 pi over 4, so this would be 8 pi over 4. And then what does that leave? Well, 13 pi over 4 minus 8 pi over 4 leaves 5 pi over 4. And so the terminal side of this angle lies in quadrant 3. And in quadrant 3, the tangent will be positive. And the reference angle will be pi over 4. And so the tangent of 13 pi over 4 is equal to positive tangent of pi over 4. Okay, and according to the table, or from the triangle, the tangent of pi over 4 is equal to 1. We want to evaluate the cotangent of negative 19 pi over 6. So I'm going to draw negative 19 pi over 6. So this would be negative 12 pi over 6. And then another negative 7 pi over 6 would give us a terminal side in quadrant 2. Another way to look at this would be to take 19 pi over 6, add 12 pi over 6 twice, which is 24 pi over 6, and get 5 pi over 6, which is a good way to check to see if you've done this correctly. Once we have this and we know we want the cotangent, then the tangent in this quadrant would be negative, and the reference angle would be pi over 6. So the cotangent of negative 19 pi over 6 would equal negative cotangent of the reference angle. So this is equal to negative 1 over the tangent of pi over 6, where the tangent of pi over 6 is 1 over the square root of 3. So what we get is negative 1 over the square root of 3, which simplifies to this.
Hi, today we're going to talk about the unit circle and how we can relate it to trigonometric functions. The unit circle is a circle of radius 1, and it has the equation x squared plus y squared equals 1. At least that's the simplest equation for it. Now, we know that the circumference of a circle is equal to 2 pi r, but in the unit circle the radius is 1, so the circumference of a unit circle is 2 pi. Now this is going to help us when we define the trigonometric functions. Before we start defining the trigonometric functions using the unit circle, we're going to define the central angle to be t radians. Now you remember that you've learned already that the arc length, the length of any intercepted arc here, is equal to r times theta. But in the unit circle, we have that r is equal to 1, and we're defining theta, the intercepted, the angle, to be t. So we have that s is equal to t. All right? So in a unit circle, now this is not any circle, but in a unit circle, the radian measure of the central angle is equal to the length of the intercepted arc. Now one thing I want to point out is that t can be any real number. You can go around this circle in either direction, positive or negative direction, and you can go around it as many times as you want. So we can define the trig functions using this because t is any real number. Now, what you've already done in trig is you have defined for general angles, we defined the sine of theta to be the value y over r, and the cosine of theta to be x over r. But in a unit circle, r is equal to 1, and that's one of the nice things about it. It makes it so useful. So r is equal to 1, and now we can define the sine of t to just be the value y, and the cosine of t to be the value x. Now remember, this is just on the unit circle. This is not for anything. Okay, so now we're able to define all 6 of the trigonometric functions using the unit circle. We have for any real number t, now remember it can be positive, it can be negative, it can be 0, and a point p, x, y that corresponds to this real number t, we define our 6 trigonometric functions as the sine of t is equal to y, the cosine of t is equal to x, the tangent of t is equal to y over x, but x cannot be 0, and then we have the reciprocal functions. Cosecant of t is 1 over y not 0, the secant of t is 1 over x, it's the reciprocal, x not equal to 0, and the cotangent is the reciprocal of tangent, x over y, with y not equal to 0. So you need to learn these 6 trigonometric functions as we proceed through the next examples. Now let's do an example. We're going to find the values of the trigonometric functions for t with a point negative 3/5, 4/5, which is on the unit circle. That's what's nice about the unit circle. It makes defining these functions very simple. we can write that the sine of t, now remember we define the sine of t to be the value of y, so the sine of t is equal to 4/5. We define the cosine of t to be x, so the cosine of t is negative 3/5. The tangent is defined as y over x. So that's, and you might remember that sine over cosine, same thing. And then that would reduce to negative 4/3. And then you can find the reciprocal functions using the definitions. Anytime you're working with functions, you need to understand and be aware of what the domain and range of the function is. We define the sine of t to be y, and we have already talked about the fact that t can be any real number. You can go around the unit circle, you can go around in positive direction, negative direction, so t can be any real number. So the domain, which is the input for a function, that's what you can put into the function, is any real number. So the domain here is going to be all reals, which we will just designate with the interval notation negative infinity to infinity, but that's all reals. Now the range of a function, that's what comes out of the function. That's the number that the function can actually equal. And if you look at the unit circle, and in general this is true for all sines and cosine functions, the value that the sine function is going to take on, the value that you put a number in, you take the sine, you get a number out, that number is always going to be between 1 and negative 1. So the range of the sine function is the interval negative 1 to 1. And the same is going to be true for the cosine function. So the domain for the sine and the cosine function is all reals. The range for the sine and the cosine function is always between negative 1 and 1, inclusive.
Let's explore the graph of the sine function, y equals sine x. Here I've made a table where x is the angle in standard position and y is the value of the sine function. Notice that all the angles in my table are special angles, so you should be able to determine all these values on your own. Then I plotted all the ordered pairs, as you can see. So now let's see what the graph of sine x looks like. Let's connect our points. So we have a nice graph of the sine function. If I had chosen values bigger than 2 pi, say 2 pi plus pi over 6, that would be 13 pi over 6. The value of the sine function of 13 pi over 6 would be what? A half, exactly. So you can see that this pattern is going to repeat itself if I had chosen values bigger than 2 pi or less than 2 pi. Now let's look at some characteristics of the sine function now that we know the graph. Here's the graph of y equals sine x. Let's look at some of the characteristics of the graph. The first thing we want to notice is what's the domain. Remember, domain means the values of x. Well, notice that the left side there's arrows, so it's going to negative infinity on the right, on the left, excuse me, and on the right it's going to positive infinity. So the domain would be all real numbers. Now let's look at the range of the function, the sine function. That's looking at the y values. What do you notice about the y values? Notice the smallest y value is negative 1. The largest y value is 1, and it takes on all values in between, so the range would be negative 1 to 1. Another thing we notice about this, there are 3 periods shown here. Here's one period, here's another period, and another period where the sine function is repeating itself 3 times. So that means the period, these intervals in between here, here's another period, and finally we have one more period drawn here. So the period for the sine function would be 2 pi. Now what that means is that if you're trying to find values, that means the sign of some value x is going to be the same thing as the sign of x plus 2 pi times, say, n, where n is any integer. They'll be the same value because the sine function is periodic. Now, another thing we notice about the graph is that its sine is an odd function. What does that mean? That means that the sine of negative x is the opposite of the sine of x. That also means that the graph is symmetric about the origin. Another characteristic, let's look at the intercepts. What's the y-intercept? Where does the graph cross the y-axis? And we can see that the y-intercept is 0. Now, what about the x-intercepts? Well, there's an infinite number of them, as we can see, because remember, this goes on forever. But let's describe where they occur. Well, let's see. One x-intercept is at 0, and then pi, and then 2 pi, and so on. Do you see the pattern? So the x-intercepts are at all multiples of pi. So we can describe that by just saying n pi, again, where n is an integer. Two more things we want to notice about the sine function. Notice that there's a maximum point and a minimum point, a relative max and a relative min. And we want to talk about where they occur. Well, we know there's an infinite number of them because the sine function repeats itself. Let's look at the relative max and talk about where they occur. The relative max occurs at what x values? Well, let's see. The first one occurs, well, not the first one, but one of them occurs at pi over 2. Where does the next one? Well, it's going to be a period away, 2 pi away. So I can describe where they occur by saying at x equal pi over 2 plus 2 pi n, where n is any integer. And then, of course, now we see there's the relative min. Where does it occur? The relative min occurs at what x value? Well, one of them is 3 pi over 2. And again, to get to the next one, we add multiples of the period. So we can say at 3 pi over 2 plus 2 pi n, again, where n is an integer. You should learn all these characteristics of the sine function. They're very important. Now we're going to focus on just one period of the sine function and look at some of those important points that you're going to need to know. Here's the graph of y equals sine x with x between 0 and 2 pi, or one period or cycle of the sine function. And we want to notice some important points on this cycle. Those important points occur at the x-intercepts and the y-intercept, which of course is the same in this case. So I've got the x-intercepts and then the points where the relative max and the relative min occur. Notice that these points occur at 1/4 of the period, so we call them quarter points. Let's list the quarter points. The first one is the origin, 0, 0. The next one is pi over 2, 1. Then pi, 0, 3 pi over 2, negative 1, and 2 pi, 0. These are important points for you to know, so you should know these quarter points for the sine function so that you can graph it easily. Let's explore the graph of the cosine function y equal cosine x. Here I've made a table of values where x is the angle in standard position in radians and y is the value of the sine function. Notice that all the angles in my table are special angles, so you should be able to get all these values on your own. Then I plotted the ordered pairs, as you can see here, so we can see what the graph of the cosine looks like. Let's connect our points. So let's see, it's going to start up at 1, go down, and do this. So I've plotted the points from 0 to 2 pi. What would happen if I chose values bigger than 2 pi or, say, less than 0? Let's take an angle. For example, 2 pi plus pi over 6 would be 13 pi over 6. What would the cosine of 13 pi over 6 be? Well, let's see, that's in quad 1. Cosine's positive, so it's going to be the square root of 3 over 2. So we can see that this pattern will just repeat itself for values bigger than 2 pi or less than 0. Now that we know what the graph of the cosine looks like, let's look at some characteristics of the graph. Let's look at the graph of the cosine function. Here I've got 3 periods of the cosine function, and we want to look at some of the characteristics. Well, the domain of the cosine function, the values of x, are all real numbers. We can see the graph goes from negative infinity to positive infinity, so the domain is all real numbers. The range will be the y values. Let's look at those. The y values go from negative 1 up to 1 and take in all values in between, so the range would be negative 1 to 1. The period is 2 pi. We can see here's a period between here. Then it repeats itself again here, so here's another period of 2 pi. And then I see another period over here. So the period for the cosine function is 2 pi. Now let's look at another characteristic, which should be, I noticed that this function is symmetric about the y-axis, which means it's an even function. That means that the cosine of negative x is the same as the cosine of x. It's symmetric about the y-axis. Next, let's look at the intercepts. Well, the y-intercept is what? The y-intercept is 1, crosses the y-axis at 1. What about the x-intercepts? Let's look at those. Where do they occur? Well, we can see we have an infinitely many of them. We can see 1, 2, 3, 4, 5, 6 here on these cycles here. But where do they occur? Well, let's see, pi over 2, then the next one's set, 3 pi over 2, 5 pi over 2, 7 pi over 2. Can you predict where the next one would be? 9 pi over 2, exactly. So you can see that they occur at odd multiples of pi over 2. How do we write that? Well, odd number is any number. 2n plus 1 gives you an odd number, and we multiply that odd number times pi over 2. That's where all the x-intercepts occur. The other thing we want to look at is the graph has relative max and relative min points, and we want to talk about where they occur. Let's look at the relative max first. Where does it occur? Well, this one's, of course, at x equals 0. And then the next one occurs 2 pi away, so we can add multiples of the period 2 pi, which is the same thing, of course, as saying 2 pi n, where n is any integer. Now let's look at the relative min. Here's a relative min. Where does it occur? At pi. Where does the next one occur? At the period away. This is an interval of 2 pi. So the relative min occurs at x equal, this would be pi plus 2 pi n, again, where n is an integer. So here are the characteristics of the cosine function that you should be very familiar with. Now I want to focus on just this one period and look at some important points. Here we have one cycle of the cosine curve, and we want to look at some important points. The important points are where the intercepts or the relative max, the x-intercepts, and the relative min. Those points occur at 1/4 of the period, so we call them quarter points. Let's list the quarter points for the cosine function between 0 and 2 pi. Well, the first one is at 0, 1. The next one occurs at pi over 2 is 0. The next point here is pi, -1, 3 pi over 2, 0, and finally 2 pi, 1. So here are the 5 quarter points for cosine x between 0 and 2 pi. You need to know these quarter points for the cosine function so you can graph it. Here we want to graph functions of the form y equal a sine x and y equal a cosine x to see what effect a has on the graph. First thing we need to talk about is the amplitude of these graphs will be the absolute value of a. It's always positive. Let's look at an example. So I have this function y equal 3 sine x. What's going to happen is this 3 is going to be multiplied by all these y coordinates of the quarter points. So you can see that I've got all those quarter points of sine x listed. So now let's figure out what the quarter points will be for 3 sine x. Well, it doesn't change the x coordinates, so they're still going to be 0, pi over 2, pi, 3 pi over 2, and 2 pi. So to get the y coordinates for 3 sine x, we're going to multiply these values by 3. So 0 times 3 is, of course, 0. 1 times 3 is 3. 0 times 3 is 0. -1 times 3, -3. And then again, 0 times 3 is 0. So here will be the quarter points for y equal 3 sine x. Let's graph that function. So we have 0, 0. Then we have pi over 2, 3. Pi, 0. 3 pi over 2, -3. And 2 pi back up to 0. So the amplitude is this distance, half the distance between the max and the min value. So let's write the amplitude for y equal 3 sine x. The amplitude will be the absolute value of 3, which is 3. Again, that's the distance, half the distance between the relative max and the relative min, which makes the range of this graph what? Exactly. The range is now going to be -3 to 3. Now let's look at another example. Let's look at the graph of y equal -2 cosine x. The amplitude will be the absolute value of -2, which of course is +2. Now, in order to graph this function, what we're going to do is multiply -2 by our y coordinates of our quarter points for y equal cosine x. So let's write the quarter points for y equal -2 cosine x. Well, the a only affects the y coordinates, so the x coordinates will not change. Okay, so let's look at the first one. So the y coordinate of cosine x is 1, multiply by -2, and what do you get? -2. It's important to note that you don't multiply your y coordinates by the amplitude, you multiply your y coordinates by a. All right, so let's keep going. 0 times -2 is still 0. -1 times -2 is +2. 0 times -2 is 0. And 1 times -2 is -2. So here are our quarter points for y equal -2 cosine x. Let's graph this function. So let's see, I have 0, negative 2, and pi over 2, 0, pi 2, 3 pi over 2, 0, 2 pi, negative 2. So here's the graph of y equal negative 2 cosine x. What is the range for this graph? Well, the range is going to be negative 2 to positive 2. So in general, when you're graphing functions y equal a sine x or y equal a cosine x, the amplitude will always be the absolute value of a, and the range will always be negative absolute value of a to positive a. Here we want to look at graphing functions of the form y equals sine bx and y equal cosine bx. For these functions, the period will be 2 pi divided by b. Now it's important to note that b must be positive here. Let's look at an example. Y equal cosine 3x. So b is positive 3, so the period's going to be 2 pi divided by 3. So b is going to change the x coordinates. Here I've listed the quarter points for y equal cosine x, which of course has a period of 2 pi. For cosine 3x, the period is 2 pi over 3. The quarter points occur at 1/4 of the period, so let's figure out what is 1/4 of this period. 1/4 of 2 pi over 3 is pi over 6. So now our x coordinates are going to be in increments of pi over 6. The y coordinates will stay the same. So let's list the quarter points for y equal cosine 3x. Okay, so the first one still occurs at 0. The next quarter point is going to be pi over 6 increments, so you're always adding pi over 6 to each x coordinate to get the next one. What is pi over 6 plus pi over 6? Well, it's 2 pi over 6, but of course you always reduce your answers. Okay, and then 2 pi over 6 or pi over 3 plus pi over 6 gives you 3 pi over 6, which is pi over 2. And finally, 3 pi over 6 plus another pi over 6 is 4 pi over 6, or the period of 2 pi over 3. So here are the quarter points for y equal cosine 3x. Let's plot those points. So we have a period of 2 pi over 3. And let's see. Notice the y coordinates are going to be 1 and negative 1. So let's see. The first point we want to plot is 0, 1. Then the next point, quarter point, is pi over 6, 0. Pi over 3, negative 1. Pi over 2, 0. And 2 pi over 3, positive 1. So here is one period for y equal cosine 3x. What is its amplitude? Well, we can see that it's still 1. Whoops. Notice that in this case a is 1, so the amplitude is 1. What is the range? Well, it's negative 1 up to positive 1. Let's look at graphing functions of the form y equal a sine bx and y equal a cosine bx. The amplitude of these functions will be the absolute value of a. The period will be 2 pi over b, again for b positive. Let's look at this example, y equals sine negative pi x. Right off the bat, we notice that our b is negative, so what do? Well, we have to remember something about the sine function, and that is that the sine is odd, and that means that the sine of negative x is the opposite of the sine of x, so we can rewrite this function as negative sine pi x. Now we can find our amplitude, which will be the absolute value of -1, which is 1. And our period for this function will be 2 pi divided by pi, which is 2. Now we want to get the quarter points for this function. We need to get 1/4 of the period to figure out the interval between the quarter points, which will be a half. So we're going to be adding a half to each of our x coordinates to get the x coordinates for y equal negative sine pi x. The first x coordinate will stay 0. Now what do we do? Let's just do the x coordinates first, and then we'll come back and do the y coordinates. So what we want to do is we want to add 1/2 to each of these x coordinates. So 0 plus a half is a half. 1/2 plus a half is 1. 1 plus a half is 3/2. And then 3/2 plus another half gives you 2. So that's our x coordinates for our quarter points. Now how do we get the y coordinates? Remember, the y coordinates are affected by a, so we want to be multiplying these y coordinates by a, which in this case is -1. So we're going to multiply each of these y coordinates by -1. So let's see, we're going to get 0. 1 times -1 is -1. 0 times -1 is 0. -1 times -1, +1, and then 0 times -1 is 0. So here are our quarter points for y equal negative sine pi x. Let's graph that function. Okay, so let's see, we have 0, 0. Then we have a half negative, oops, not pi over 2. Should have been a half. So all of these should be a half, 1, 3/2, and 2. So this point, 1/2 -1 down here, 1/2 0, 1 0, 3/2 +1, and then 2 0. So here would be 1 period for the function y equal negative sine pi x. Notice that it's going down first. There's the negative, which reflects it about the x-axis. What's the amplitude? We said was 1. What's the range for this function? Let's write that down. The range would be -1 to +1. Let's take a look at graphing y equal -2 cosine of -4x. Again, the first thing I need to notice is when b is negative. To find the period, you need a positive b. So we need to rewrite this function. Remember that the cosine is even. Let's see. What does that mean? It means that the cosine of -x is the same as the cosine of x, which means the cosine of -4x is the same as the cosine of 4x. So this can be rewritten as y equal -2 cosine of 4x. Now, what's the amplitude? Well, the amplitude is going to be the absolute value of -2, which of course is +2. What's the period? Well, we find the period by taking 2 pi, dividing by b, which in this case is 4. So our period will be pi over 2. Now, how do we get our x coordinates? We need to know the 1/4 of the period. And what is 1/4 of pi over 2? Well, that's pi over 8. So pi over 8 is going to be what we add to each x coordinate to get our x coordinates for our quarter points for this function. So let's write those down. So let's say we have -2 cosine 4x. The first x coordinate will stay 0. Now, what do we add to 0 to get to the next one? You add pi 8. So this next x coordinate will be pi over 8. So again, you're adding pi over 8 to each x-coordinate. What's this x-coordinate going to be? Well, what is pi over 8 plus pi over 8? Well, that's 2 pi over 8, which you reduce to pi over 4. And then keep adding pi over 8. That's 2 pi over 8 plus pi over 8 gives you 3 pi over 8. And then 3 pi over 8 plus another pi over 8 gives you 4 pi over 8, which of course is pi over 2. So those are our x-coordinates for our quarter points. How do we get our y-coordinates? Well, we need to multiply each of these y-coordinates by a, which is negative 2. Make sure you don't multiply by 2. It's always a, not the amplitude. So let's see. What is 1 times negative 2? Negative 2. 0 times negative 2 is 0. Negative 1 times negative 2 is a positive 2. 0 times negative 2 is 0, and 1 times negative 2, negative 2. So here are our quarter points for y equal negative 2 cosine 4x. Let's look at that graph. So we have 0, negative 2, pi over 8, 0, pi over 2, positive 2, 3 pi over 8, 0, and pi over 2, negative 2. So here would be one period for this function y equal negative 2 cosine 4x. We figured out the amplitude for this function was 2. What's the range for this function? Well, the range is going to be negative 2 to 2. Remember, it's always negative absolute value of a to positive absolute value of a. In this example, we're given a graph and we want to determine the equation of a function of the form y equal a sine bx or y equal a cosine bx. So we have to decide whether we're going to use a sine function or a cosine function. Well, how do we know? Let's look at the first quarter point. It's 0, 0. It goes through the origin, so we know we're going to use a sine function. So we're going to write y equal a sine bx. So now we have to find b and a. Well, remember, b is with the period, so let's look at this graph. What's the period for this graph? We can see the period is 8 pi. So let's write that down. And how do we get the period? Do you remember? That's right, you take 2 pi and you divide by b to get the period. So we can solve for b, multiply both sides by b. So we get 2 pi divided by 8 pi, which is 1/4. So now we know b is 1/4. Now we need to find a. Well, I can see from the graph that the amplitude is 2, but that doesn't mean that a is 2. Notice that this graph is decreasing first. This y-coordinate of this quarter point is negative 2. So I know a is negative 2. So now what's our sine function? Y equals negative 2 sine of 1/4 times x. You need to practice working these examples until you've mastered the skills and concepts involved. Let's take a look at graphing functions of the form y equals sine x minus c and y equal cosine x minus c. In these forms, c shifts your graphs horizontally to the right or the left. Let's look at our basic cosine curve. We know what it looks like. The period is 0 to 2 pi. So if c is positive, it's going to take our graph and shift it to the right c unit. So the first x-coordinate of the quarter point in this case would be c, and then the last x-coordinate would be c plus 2 pi. If c is negative, you're going to shift to the left, and so your first x-coordinate of your quarter point will be c, and again, the period's 2 pi, so the last x-coordinate will be c plus 2 pi. Let's look at an example. Let's look at y equals sine x minus pi over 2. Well, we know what our basic sine curve looks like. I've listed the quarter points for y equals sine x. So here, remember the amplitude is going to be the absolute value of a, which is 1 in this case, so the amplitude is 1, and the period is 2 pi over b, and notice in this case b is 1, so the period is still 2 pi. But the graph is going to be shifted pi over 2 to the right, so that means that the first x-coordinate of the quarter point is going to be pi over 2. So let's figure out all the x-coordinates. So since the period is 2 pi, 1/4 of that period is pi over 2. That's going to represent the interval between each x-coordinate. So what we're going to do is we're going to add pi over 2 to each of these x-coordinates to get our next x-coordinate. Pi over 2 and pi over 2 is pi. Pi plus pi over 2 is 3 pi over 2. 3 pi over 2 plus pi over 2 is 2 pi. And 2 pi plus pi over 2 would be 5 pi over 2. So again, all we're doing is we're adding 1/4 of the period to get these x-coordinates. Now the y-coordinates haven't changed at all, so we're going to have pi over 2, 0, pi 1, 3 pi over 2, 0, 2 pi negative 1, 5 pi over 2, 0. So the graph is going to look like this. Pi over 2. So let's see, pi over 2, 0, pi 1, 3 pi over 2, 0, 2 pi negative 1, 5 pi over 2, back to 0. Okay, here we've drawn one cycle or period for this function, and of course the domain's all real numbers, so it's going to continue in both directions. Let's look at sketching graphs of functions of the form y equal a sine bx minus c and y equal a cosine bx minus c. I've listed the characteristics of the graphs here in this box. And I want to show you why the period is 2 pi over b and the phase shift is c over b. The first thing I want to talk about is b. You need to make sure that b, the coefficient of x, is positive first. If it's not, you're going to rewrite the function using even-odd properties to make b positive. So let's also remember, if you recall, when you're graphing y equal a sine x and y equal a cosine x, recall that the period for those graphs is 2 pi, so that means they complete one cycle when x is between 0 and 2 pi. Well, graphs in either one of these forms will complete one cycle when bx minus c is between 0 and 2 pi. So let's set that up. So we have bx minus c between 0 and 2 pi. And we've made b positive, remember, by even-odd properties if we need to. Now we're going to solve this for x. So let's add c to both sides. And divide by b. So what we can see here is that graphs in either one of those forms are going to complete one cycle when x is on the interval c over b to 2 pi over b plus c over b. That's when it will complete one cycle. Well, the length of that cycle is the period. So the period is going to be when you take 2 pi over b plus c over b. If you subtract c over b, we can see that we get 2 pi over b. So the period is 2 pi over b. And we can see here that this expression right here is the phase shift. Remember, the first quarter point of those functions used to start at 0. Now it's going to start at c over b. So we call c over b the phase shift. So the phase shift is c over b, period is 2 pi over b, amplitude is absolute value of a, and the range is negative absolute value of a to the positive absolute value of a. Let's look at an example. Here I want to sketch the graph of y equal 4 cosine 2x plus pi. Now, I need to figure out what's the amplitude. Well, remember the amplitude is the absolute value of a, which in this case is 4, The range then is going to be -4 to 4. The period is going to be 2 pi over b. Okay, let's look in this example. What's b? Notice that b is positive. b is 2. Oops, 2. Sorry about that. 2 pi over 2. So the period for this graph is pi. And what's the phase shift? Well, the phase shift is going to be c over b. Now notice that I see a plus sign. If you like, you can actually factor out the 2. If I factor out the 2, I'm going to have x minus a pi over 2. Whoops, I need a 2 minus a negative. There we go. So I'm just changing the plus sign to subtracting. So this is x minus, I can see here, this is my phase shift. Okay. Some students like to factor out the b. Some students just like to use the formulas, whichever works for you. So I know that the period is pi, and the phase shift is, we said c was a negative pi over 2. So the phase shift is negative pi over 2. Okay, so now we need to figure out the quarter points for this graph. Well, I've listed the quarter points for y equal cosine x. B and C are going to change the x coordinates of those quarter points. So remember, it used to start at 0. Well, now it's going to start at the phase shift, which is negative pi over 2. Now, how do I get the next x coordinate? Remember how to do that? You take 1/4 of the period. Well, 1/4 of the period is just pi over 4. So I want to be adding pi over 4 to each of these x coordinates. Well, negative pi over 2 is negative 2 pi over 4. If you add pi over 4, you're going to get negative pi over 4. And again, add pi over 4 to negative pi over 4, you get 0. Add pi over 4 to 0, you get pi over 4. And lastly, add pi over 4 to pi over 4, you get 2 pi over 4, which is pi over 2. So now we found all the x coordinates. How do we find the y coordinates? Well, the y coordinates are found by taking the y coordinates of these quarter points and multiplying by a, which in this case is 4. So let's see, 1 times 4 is 4. 0 times 4 is 0. Negative 1 times 4, negative 4. 0 times 4 is still 0, and then 1 times 4 is 4. So now we found our quarter points. We can plot those points. So let's see, negative pi over 2. And then I need 4 and negative 4. And so we have negative pi over 2, 4, 0, negative 4, 0, back up to 4. All right, so here's one cycle for this particular function. And of course, the domain's all real numbers, so it's going to keep going in either direction. Let's look at another example. In the previous example, we had y equal 4 cosine 2x plus pi. We can rewrite this as 2x minus a negative pi so that we can see the a is 4, the b is 2, and the c is negative pi. Well, in our next example, y equal 2 sine negative 4x plus pi, we need to rewrite it for a different region. Let's write down this function. We have 2 sine negative 4x plus pi. Well, I see a plus sign here and I see a plus sign here, but it turns out the phase shift is not negative because, more importantly, I have b that's negative. And whenever b is negative, your first step is to rewrite it using even-odd identities. If you recall, the sign is odd, which means what? It means the sign of negative x is negative sine x. So what I can do is I can factor that negative out, and then I actually have 4x minus pi. And then using even-odd identities, this is equal to negative 2 sine of 4x minus pi. So now I can see that my A is negative 2, my B is 4, and my C is pi. So now let's figure out the amplitude. Well, the amplitude is going to be the absolute value of A, which absolute value of negative 2 is 2. The range is going to be negative 2 to 2, period. It's going to be 2 pi over B. My B, remember, is 4. So that's pi over 2. And my phase shift is C over B. So it's positive this time. Okay, so now look at, we have the quarter points for y equals sine x. We know what those are. You should know those very well. So how do we get the quarter points here? Well, the x-coordinates, the first x-coordinate starts at your phase shift. So pi over 4 is the first x-coordinate. Now how do we get the next one? Do you remember? Exactly. You have to take 1/4 of the period, which is pi over 8. So this time I want to add pi over 8 to each of the x-coordinates. So let's see. Pi over 4 is the same thing as 2 pi over 8. Plus pi over 8 gives you 3 pi over 8. 3 pi over 8 plus pi over 8 is 4 pi over 8, which reduces to pi over 2. 4 pi over 8 plus pi over 8 is 5 pi over 8. And last x-coordinate, 5 pi over 8 plus pi over 8 gives you 6 pi over 8, which reduces to 3 pi over 4. Okay, now how do we get the y-coordinates? Remember, to get the y-coordinates, you multiply these y-coordinates by A. And be careful, remember A is negative 2. So 0 times negative 2 is still 0. 1 times negative 2. 0 times negative 2. Negative 1 times negative 2. And 0 times negative 2. So now we can plot these points. Let's see. Let's make this pi over 8. So pi over 4 here. 3 pi over 8. Pi over 2. And 3 pi over 4. And then we have... Okay, so our first point, pi over 4 is 0. And then it's decreasing first. So 3 pi over 8, negative 2, back to 0, 2, back to 0. And of course, since we have one cycle, we can continue this graph in either direction. It's going to just continue the graph. So remember, very important when B is negative that you rewrite it first to get B positive. Let's look at sketching graphs of functions of the form y equal a sine bx minus c plus d and y equal a cosine bx minus c plus d. You may recall from algebra that when you add a constant to a function, it shifts the graph vertically. Same thing's going to happen here. So remember your quarter points for a sine bx minus c. Well, all you're going to do, you're going to add d to the y coordinates of all the quarter points of this function. Or of course, if it's a cosine, you're going to add d to all the quarter points of a cosine bx minus c. Now, remember we're shifting vertically, so that's actually going to change the range. Remember the range, when we don't have a d, when d is 0, is negative absolute value of a to a. So to get the range for functions in this form, we have to add d to get the range. We have to do negative absolute value of a plus d, so you're adding d to all the y coordinates to absolute value of a plus d. Period and phase shift do not change. Let's look at an example. I have y equal 3 cosine 6x minus pi plus 2. So here I can see that a is 3, so I know my amplitude is 3. Absolute value of 3 is 3. But what's the range? Well, remember the range is going to be negative 3, and then we have to add 2 to positive 3 plus 2, so the range is negative 1 to 5. The period is going to be 2 pi over b. Okay, so my b is 6, my c is pi, and my d is 2. So let's see, 2 pi over 6. My period's going to be pi over 3. And my phase shift is going to be c over b, so pi over 6. Now, I've listed the quarter points for y equal cosine x. Let's get the quarter points for this function. The first x coordinate is your phase shift, so pi over 6. Now, remember what you add to each of these quarter points. We need to find 1/4 of the period. 1/4 of pi over 3 is pi over 12. So what I want to add to each of these x coordinates is pi over 12. Think of pi over 6 as 2 pi over 12. When you add pi over 12 to 2 pi over 12, you get 3 pi over 12, which reduces to pi over 4. 3 pi over 12 plus pi over 12 is 4 pi over 12, which reduces to pi over 3. And 4 pi over 12 plus pi over 12 is 5 pi over 12. And then 5 pi over 12 plus pi over 12 gives me 6 pi over 12, which reduces to pi over 2. So notice that my x coordinates are affected by b and c. Now we need to get the y coordinates. Well, remember, when we didn't have a d, we got the y coordinates by multiplying my y coordinates by a. Well, now we multiply our y coordinates by a, but then we add 2. So let's go. A is 3, so we're going to do 1 times 3 is 3, plus 2 gives me 5. 0 times 3 is 0, plus 2 is 2. Negative 1 times 3 is negative 3, plus 2 is negative 1. 0 times 3 is 0, plus 2 is 2. And finally, 1 times 3 is 3, plus 2 is 5. So let's plot these quarter points. And let's see, I need to go up to 5 and down to negative 1. Okay, so we have pi over 6, we're up at 5. Pi over 4, we're at 2. Pi over 3, we're down at negative 1. Back to 2, and back to 5. All right. So here's one cycle for this function. Of course, domain is all real numbers, so it doesn't stop. It continues in both directions forever. So I want to reiterate. To get your x coordinates, you find the phase shift, then you add 1/4 of the period. To get your y coordinates, you multiply the old y coordinates by a, and then you add d. Suppose we want to determine the equation of a function given the graph. Look at this graph. Suppose we were asked to choose an equation of a function from this list below that matches this graph. Take a minute and you'll realize that all 5 of these equations match this graph. So we're going to have to know more information in order to determine a unique function. Let's look at this example here. We're given the graph and we want to determine the equation of a function of the form, and we're going to be told it's a cosine curve, and we're going to be told b is positive. And also we're going to associate these 5 labeled quarter points with the 5 quarter points for y equal cosine x over the interval 0 to 2 pi. Well, let's write those quarter points down. We should know what they are. For y cosine x, those quarter points are 0, 1, pi over 2, 0, pi, negative 1, 3 pi over 2, 0, 2 pi, 1. And we can see the quarter points for this one. Pi over 6, negative 4, pi over 3, 0, pi over 2, 4, 2 pi over 3, 0, and 5 pi over 6, negative 4. So This quarter point is associated with this one and so on. So what this tells me, I can see that the phase shift is pi over 6. Also, we can figure out the period because the first quarter point is pi over 6. Well, the first x-coordinate of the quarter point is pi over 6, and the x-coordinate of the last quarter point is 5 pi over 6. The difference between those two x-coordinates gives us the period, so we can figure out the period. We can take 5 pi over 6 and subtract pi over 6 to get 4 pi over 6. And reduce that, that's 2 pi over 3, so I know what my period is. Now, do you remember how to find the period? Exactly, so to get the period, you take 2 pi and divide by b. Remember, we're assuming b is positive this time. So we can easily see that in this case, b is 3. Okay, so now we know b. We want to come up with c and a. Well, remember, we know the phase shift is pi over 6. And remember, to get the phase shift, you take c over b. So I know c over b is pi over 6. And we just found that b was 3, so we know c over 3 is pi over 6. We can solve this for c. So c is going to be 3 pi divided by 6, which is pi over 2. So we know b, we know c, we need to find a. Well, looking at this graph, we can easily determine the amplitude is 4. But be careful, a is not positive 4. Notice that this cosine is increasing first, which tells me that a is negative 4. So now we can write our function. A is negative 4, b was 3, and c was pi over 2. So we can determine a unique function if we make the assumptions. We're going to be told whether it's a sine or cosine. In this case, it's a cosine. We're going to be told b is positive, and we're going to be given 5 quarter points of one cycle that associates and corresponds to the quarter points, in this case for y equal cosine x, for x between 0 and 2 pi. Practice working these examples until you've mastered the skills and concepts involved. Let's take a look at the tangent function. Recall that the quotient identity for tangent x is equal to sine x over cosine x, which tells us that the tangent function will be undefined when the cosine x is equal to 0. Let's see when that happens. The cosine is equal to 0 when x is equal to 2n plus 1 over 2 times pi, which is another way of saying odd multiples of pi over 2. So as you can see in my table, I know that this function is going to be undefined at pi over 2. Some other values, remember it's odd multiples of pi over 2, so that would be 3 pi over 2, 5 pi over 2, negative pi over 2, and so on. Next, the tangent function will be equal to 0, or the x-intercepts, when the sine function is equal to 0. Let's see when that happens. Well, the sine is equal to 0 when x is equal to n times pi. And again, in both of these cases, n is any integer. So that means that the zeros or x-intercepts will occur at 0, pi, 2 pi, negative pi, and so on. So you can see in my table I've got the value of 0, 0. So now I've listed some values for tangent function. The first 4, you should know these are special values. So and I've plotted those points on my graph. What we want to see is that when we choose x values closer and closer to pi over 2, the values of the tangent function increase without bound, which means that there's a vertical asymptote at pi over 2. So let's put that on our graph. And so we know that this graph from 0 to pi over 2 looks like this. Now, tangent function happens to be odd. Let's see why. If I look at the tangent of negative x using the quotient identity again, that's going to be the sine of negative x over the cosine of negative x. And you need to recall that, remember, the sine function is odd, which means the sine of negative x is negative sine x. Cosine function, remember, is even, which means the cosine of negative x is the same as the cosine of x. And I can see that that's going to equal negative tangent x. So we know the tangent function is odd. What does that mean? It means that the graph is symmetric about the origin. So we can get another piece of the graph. So remember, it's undefined at negative pi over 2. And if I reflect this part about the origin, the graph looks like this. So here's one cycle or period for the tangent graph between negative pi over 2 and pi over 2. We call this cycle the principal cycle. And there's a couple of key special points that you need to know for this graph. Let's draw those points right now. So at pi over 2 and negative pi over 2, the tangent function is undefined. It's 0. The origin is one of the special points. The point pi over 4, 1, is an important point, as well as negative pi over 4, negative 1. So this graph you should know very well. It shows where the asymptotes are. It shows these 3 points. We call this the center point. It's obviously in the center of the cycle. These 2 points, we call them halfway points. And of course, this is another halfway point. And this, of course, is the center point. So you need to know negative pi over 4, negative 1, 0, 0, pi over 4, 1 for the tangent function and the asymptotes at negative pi over 2 and pi over 2. So now that we know that what one cycle looks like, let's look at some more cycles and come up with some characteristics for the tangent function. Here I've drawn 3 cycles for the tangent function, and we want to look at some of the characteristics of the graph. The first thing we want to observe is what the domain is. The domain is all real numbers x, such that x cannot equal 2n plus 1 over 2 times pi, where n is any integer. Again, that's saying all odd multiples of pi over 2. It's undefined, so that's the domain. So you can see at pi over 2, 3 pi over 2, those are values that are not in the domain. The range of the function, look at the y values, is negative infinity to infinity. The period, here we have 3 periods. Here's another one. Period is pi. And the principal cycle we will call from negative pi over 2 to pi over 2. So these are very important concepts that you need to know about the tangent function. Let's look at some more. The tangent function, remember, is undefined. And where it's undefined, there are vertical asymptotes. They occur where x is equal to 2n plus 1 over 2 times pi. Again, odd multiples of pi over 2. Look at the graph. Have a vertical asymptote of pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2. The next one would be at 5 pi over 2. The y-intercept, we can see, is at the origin. The y-intercept is 0. For each cycle, there are 3 important points. One of them is called the center point. So on these periods, I can see I have a center point at 0, 0, center point at pi 0, center point at negative pi 0. The x-coordinates of those center point, the x-intercepts or the zeros are of the form n pi, again, where n is any integer. So again, 0, pi, negative pi, 2 pi. And the y-coordinate of all those center points is 0. Next, we have halfway points. For each cycle, there are 2 halfway points. The halfway point to the left of the center point is located midway between the x-coordinate of the left vertical asymptote and the x-coordinate of the center point. and the y-coordinate of that center point to the left is -1. The halfway point to the right of the center point is located midway between the x-coordinate of the center point and the x-coordinate of the right vertical asymptote, and the y-coordinate of those halfway points is 1. Next, we see that the tangent function is odd. That means the graph is symmetric about the origin. And lastly, the graph of each cycle we can see is 1 to 1. Remember your horizontal line test. If I look at one cycle, it passes the horizontal line test. So each cycle is 1 to 1. You need to be very familiar with these characteristics and be able to graph one period for the tangent function. Let's take a look at sketching functions of the form y equal a tan bx minus c. Recall that the principal cycle for y equal tangent x was -pi/2 to pi/2. When you're sketching functions in this form, the principal cycle will occur when bx minus c is between -pi/2 and pi/2. So in this example, we have y equal 2 tan x minus pi/4, and we want to sketch this graph. So the first thing we're going to do is notice that b is positive. In this case, b is 1. C is pi/4. If b is negative, you would have to rewrite it. Remember that the tangent function is odd to make the b positive, and then you would begin. So in this case, our b is positive. So we take our bx minus c, which in this case is x minus pi/4, and we put it between -pi/2 to pi/2 to determine the principal cycle for this function. So we want to solve for x, so we want to add pi/4 to each side, so that would give me -pi/4 less than x. Pi/2 plus pi/4 would be 3 pi/4. So here's what I know. I know the principal cycle for this function is going to be -pi/4 to 3 pi/4. Notice that the period, the length of that interval, is still pi. You can always find the period by taking pi and dividing by b. Remember, the normal period for tangent is pi, and of course in this case b is 1. So we can see the period is pi. So now we know the principal cycle. We can figure out where the left and the right vertical asymptote occur for this principal cycle. The left vertical asymptote is going to be at x equal -pi/4, and the right vertical asymptote will occur when x is equal to 3 pi/4. So let's go ahead and put that on our graph. So let's see, we have -pi/4 and 3 pi/4, and I know those are where my vertical asymptotes are. Next, we need to find those 3 key points. Let's start with the center point. Recall that the center point is located, the x-coordinate is going to be located midway between the x-coordinate of the left vertical asymptote and the x-coordinate of the right vertical asymptote. So that means our x-coordinate will be, you can add up these coordinates and divide by 2, which gives me 2 pi/4 divided by 2, which is pi/4. So the x-coordinate of the center point is pi/4. The y-coordinate of the center point is 0. So the point that I have now, my center point, let's write it up here, is pi/4, 0. So let's go ahead and plot that point. Pi/4, 0 is my center point. Next, we need to find the 2 halfway points. Let's find the halfway point to the left of this center point. To get the x-coordinate of the halfway point to the left, it's going to be located halfway between this left vertical asymptote and the x-coordinate of the center point. So the x-coordinate will be negative pi over 4 plus pi over 4. And again, you divide that by 2. Well, the numerator is 0. 0 divided by 2 is 0. The y-coordinate. Well, remember the y-coordinate for the normal tangent was going to be down at negative 1. So what you do to get the y-coordinate of this halfway point, you're going to multiply that y-coordinate of negative 1 for the basic tangent, and you're going to multiply it by a. Notice in this case my a is 2, so I'm going to do negative 1 times 2, which gives me negative 2. So this halfway point would be 0, negative 2. Now we need to find the halfway point to the right of the center point. Well, again, the x-coordinate will be located midway between this x-coordinate of the center point and the x-coordinate of the right vertical asymptote. So that's going to be pi over 4 plus 3 pi over 4. And again, divide by 2, so that gives you pi divided by 2 is going to be the x-coordinate of this halfway point. The y-coordinate is going to be, recall the y-coordinate to the right of the normal tangent, y equal tan x, is positive 1. So you're going to multiply that positive 1 times a, which in this case is 2. So the y-coordinate of this halfway point is going to be 2. So this point will be pi over 2, 2. So we'll plot that point. So I can see that this sketch, the graph will look like this. This is what this one cycle will look like for this particular tangent function. Very important that you remember how to find these points and how you find the principal cycle and the left and the right vertical asymptotes. Let's look at this example. We have y equal negative tan, parentheses 1/2 x plus pi. We want to sketch this graph. The first thing we want to determine is the principal cycle. The principal cycle will occur when bx minus c, which in this case is 1/2 x plus pi, is between negative pi over 2, which recall is the negative pi over 2 to pi over 2 was the principal cycle for tangent. Now we want to solve this for x. So first I want to subtract pi. So let's see, now I need to multiply by 2. So now I know that the principal cycle for this function is negative 3 pi to negative pi. Now that I know the principal cycle, I know that the left vertical asymptote is x equals negative 3 pi, and the right vertical asymptote will be x equals negative pi. So again, to determine the principal cycle, you take the argument bx minus c, you put it between negative pi over 2 and pi over 2, you solve. That will give you the principal cycle. The left of the principal cycle tells you the left vertical asymptote, and at the right gives you the right vertical asymptote. Now let's find the 3 special points. Let's find the center point first. Well, recall the center point is located midway between the left and the right. The x-coordinate between the x-coordinate of the center point is located midway between the left and the right vertical asymptote. So, whoops, negative pi. So if I take negative 3 pi plus a negative pi divided by 2, that gives me negative 2 pi for the x-coordinate of the center point. And the y-coordinate of the center point is 0. So my center point, let's write, is negative 2 pi, comma 0. So let's go over to our graph and let's show what we have so far. Let's put in the left vertical asymptote, so let's say that's negative pi. Let's say this is negative 3 pi. So I know I have a vertical asymptote here and here. And I know the center point is negative 2 pi 0. Now we need to find the halfway points. Well, the halfway point to the left of the center point, the x-coordinate is located midway between this vertical asymptote and the x-coordinate of this center point. So that will be, the x-coordinate will be negative 3 pi plus a negative 2 pi, or negative 2 pi divided by 2. Well, that's negative 5 pi over 2 is the x-coordinate of this halfway point. The y-coordinate, we have to remember what the principal cycle for tan x. Remember, the halfway point to the left on y equal tan x, the y-coordinate to the left of the center point is negative 1, so we take that negative 1 value and multiply it by our a. Notice in this case, our a is negative 1. So we have a negative 1 times a negative 1, which of course is 1. So this halfway point is negative 5 pi over 2, comma, positive 1. So let's show that. Okay, now we have one more halfway point to find, the one, of course, to the right of the center point. Its x-coordinate is going to be located midway between the x-coordinate of the center point and this vertical asymptote, so that's going to be negative 2 pi plus a negative pi, or negative pi over 2. That's negative 3 pi over 2 is the x-coordinate of this halfway point. And the y-coordinate you find by taking the y-coordinate for the basic tan x, which is positive 1 times a. And again, a is negative 1, so the y-coordinate of this halfway point is negative 1. So this point would be negative 3 pi over 2, negative 1. Let's plot that point. Okay, so now we've got center point, our halfway points, our vertical asymptotes. So here is one cycle for this tangent function. Let's take a look at the cotangent function, y equal cotangent x. First thing I want to use is, remember that the cotangent function used in the quotient identity is the same thing as cosine x over sine x. So this means the cotangent function will be undefined when sine x is equal to 0. And when does that happen? That occurs when x is equal to n times pi, where n is an integer. So it's undefined, for example, it's 0, pi, 2 pi, negative pi. I've listed those in my table. The next thing is it's equal to 0, or the x-intercepts occur when cosine x is equal to 0. And that occurs when x is equal to 2n plus 1 over 2 times pi, or odd multiples of pi over 2. So at pi over 2, it's 0. The next one would be 3 pi over 2, 5 pi over 2, and so on. So I've got that point. Pi over 4 and 3 pi over 4, those are some special values you should know. The cotangent of pi over 4 is 1. The cotangent of 3 pi over 4 is negative 1. So I've plotted those 3 points. Where the cotangent function is undefined, that's where your vertical asymptotes will be. So there's one here on the y-axis, and there's one here at x equals pi. So the one cycle for this cotangent will look like this. We can see the length of that interval is pi. So the period is pi. And we call this cycle from 0 to pi, we call this the principal cycle for cotangent. You need to know where those asymptotes are. And then let's look at these points. there are 3 special points for the cotangent. We have the center point located at pi over 2, 0. We have a halfway point to the left of that, pi over 4, 1. And our other halfway point to the right of the center point is 3 pi over 4, negative 1. It's very important that you learn this graph, that you can draw one cycle, including the asymptotes and the 3 important points. Here I've drawn 3 cycles for the cotangent function, and we want to look at the characteristics of the cotangent function. The first is the domain. That's the values of x. X can be any real number except n pi, where n is any integer. So that means, for example, it's undefined at 0, pi, 2 pi, negative pi, and all multiples of pi. So that's the domain. Next, let's look at the range, the y values. Well, we can look at a cycle and we can see that the y values go from negative infinity to infinity. The period for the cotangent function we can see is pi. This is what we call the principal cycle. But we can see another period over here. And so you need to know that the period for cotangent is pi. And you need to know that the principal cycle for the cotangent function is 0 to pi. From here to here is the principal cycle. Now let's look at some other characteristics. Because it's undefined, there's vertical asymptotes at all values x equal n pi. So on this graph you can see I have a vertical asymptote at x equals 0, x equals pi, x equals 2 pi, and x equal negative pi. All multiples of pi there will be vertical asymptotes, and you need to know where they occur. We can see from the graph that there's no y-intercept since x cannot equal 0. Now, for each cycle, there are 3 special points, and you need to learn these points and be able to plot them. Let's talk about the center point first. The center point is located halfway between the left vertical asymptote and the right vertical asymptote. So the x-coordinate is right in the middle between the left and the right vertical asymptote. And the y-coordinate of the center point is 0. So all of these, you can see 3 center points. They always occur. The x-coordinate is midway between the left vertical asymptote and the right vertical asymptote. And the y-coordinate is always 0. Now let's look at the halfway points for each cycle. Let's look at the halfway point to the left of the center point. Let's look at this one. The x-coordinate of this halfway point is located midway between the left vertical asymptote and the x-coordinate of the center point, and the y-coordinate of that halfway point is 1. Next, let's look at the halfway point to the right of the center point. Let's look at this one. Its x-coordinate is located midway between the x-coordinate of the center point and the right vertical asymptote, and the y-coordinate of this halfway point is negative 1. So you need to know how to plot and find those halfway points and center points. Next, we can see that the graph of the cotangent is odd. I can see that the graph is symmetric about the origin. Remember, because it's odd, that means that the cotangent of negative x is the opposite of the cotangent of x. And lastly, we can see that for each cycle for the cotangent function, that it passes the horizontal line test, which means that for each cycle, the cotangent function is 1 to 1 on each cycle. You need to learn all these characteristics of the cotangent function and be able to graph at least one period showing the asymptotes and showing the center point and the halfway points. Let's take a look at sketching functions of the form y equal a cotangent bx minus c. In this example, we want to sketch the graph of 3 cotangent x plus pi over 3. When you have functions in this form, the first thing you want to note is if b is positive. If b is not positive, then you would rewrite this function using the fact that the cotangent is odd. In this case, I can see my b is 1, so we don't need to rewrite it. Recall that the cotangent function, the principal cycle for y equal cotangent x, was between 0 and pi. So in order to find the principal cycle for functions in this form, we're going to let bx minus c, in this case x plus pi over 3, we're going to put it between 0 and pi, and this will give us the principal cycle for this function. Solving for x, subtracting the pi over 3, we can see that the principal cycle for this function is negative pi over 3 to 2 pi over 3. Now the length of that interval would be the period, and the length of that period, that interval is pi. We can always find the period by taking pi, the normal period for cotangent x, and dividing by b. In this case, b of course is 1, so I can see that that's pi. Now that we have the principal cycle, we can find the left vertical asymptote and the right. The left vertical asymptote will occur when x is equal to negative pi over 3, and the right vertical asymptote would be when x is equal to 2 pi over 3. Now we want to find the center point. Well, the center point is located midway between the left and the right vertical asymptote. Let's go ahead and put our asymptotes on the graph now. So we have negative pi over 3. Let's see, if this is 2 pi over 3, then about right here. So I have an asymptote here, and I have an asymptote here. So the center point is located midway between the left and the right vertical asymptote. Let's find the x-coordinate. Well, I don't need a right coordinate. Let's just do x equals. So the x-coordinate will be negative pi over 3 plus 2 pi over 3 divided by 2. So that's negative pi over 3 divided by 2 is pi over 6. And the y-coordinate of this center point is 0. So the center point is pi over 6, comma 0. So remember, it's midway between, so let's try to eyeball. That looks about right. So pi over 6, 0. That's my center point. Now we need to find the halfway points. Well, let's find the halfway point to the left of the center point. The x-coordinate to the left of this center point is located midway between the left vertical asymptote and the x-coordinate of the center point. Well, let's see what we get. That's negative 2 pi over 6, so negative pi over 6 divided by 2 is negative pi over 12. Now we need to find the y-coordinate. Well, in order to find the y-coordinate, we have to recall, when you look at the graph of y equal cotangent x, the y-coordinate to the left has a y-coordinate of positive 1. So we want to take that y-coordinate of 1, and we want to multiply it by a. In this case, my a is 3. So I want to do 1 times 3, which of course is 3. So this halfway point is negative pi over 12, 3. So looks about right here, negative pi over 12. And we want to be up at 3. Now we need to find the halfway point to the right of the center point. Well, the x-coordinate, this halfway point is going to be located midway between the x-coordinate of the center point and the right vertical asymptote. So let's see what that gives us. Pi over 6 plus 2 pi over 3 is the same thing as 4 pi over 6. So I have pi over 6 plus 4 pi over 6 is 5 pi over 6. Well, that gives me 5 pi over 12 is the x-coordinate. And then to find the y-coordinate, we need to remember again the y-coordinate for the halfway point for the basic cotangent is -1. So we need to do -1 times our a. And again, my a is 3. So this will be -3. So this halfway point is 5 pi over 12, -3. And it's located halfway between there. So this would be 5 pi over 12, and then I need -3. So this is the sketch of this particular cotangent function. Once again, for cotangent, it's very important that you remember that your bx plus c has to be between 0 and pi, because that's the principal cycle for the normal cotangent. Also, make sure you know how to find the center point and the halfway points. Let's take a look at the cosecant function. Recall that the cosecant function is the reciprocal of the sine function, so it's equal to 1 over the sine of x. In order to get the graph of the cosecant, what we're going to do is first look at the sine function and then use reciprocal identities. So let's do this first. Let's lightly sketch the sine function over here. You should remember the sine function very well. Its period is 2 pi. It's 0, 0, pi over 2, 1, pi 0, 3 pi over 2, -1, and then 2 pi back to 0. Of course, we can draw another period. Okay, so we've sketched the sine x, 2 periods for the sine x. If the cosecant, which it is, the reciprocal of the sine function, first of all, notice that the cosecant function is going to be undefined when the sine of x is 0. And the sine of x is equal to 0, we can see, when x is equal to n times pi, where n is an integer. Now, when the sine of x is 0, that's going to give you your vertical asymptote. So we know at all multiples of n pi, there's going to be vertical asymptotes. So I know there's going to be an asymptote here on the y-axis, here at pi, here at 2 pi, negative pi, and then negative 2 pi. Now, notice that the maximum point for a sine function is pi over 2, 1. The reciprocal of 1 is 1, so this point will also be a point on the cosecant function. Look at all these values for sine x between 0 and pi, the sine function. The values are between 0 and 1. If you take the reciprocal of those values, you get numbers bigger than 1, and it has to approach those asymptotes. So this portion of the graph looks like this. Similarly, over here at 3 pi over 2, the sine function is -1. The reciprocal of -1 is also -1. So this is going to be a point on the cosecant function. And all these values of sine between -1 and 0, the reciprocal of those values are numbers less than -1. And it, of course, approach the asymptote. So this portion, the cosecant graph, looks like this. So here's one cycle. Let's draw another one. Now let's look at some characteristics of the cosecant function. Let's look at the characteristics of the cosecant function. First of all, remember that when the sine of x is 0, it's undefined, so the domain is all real numbers except x equal n pi, where n is an integer. The range, so the domain, all real numbers except n pi. The range, we need to look at the y values. So let's look at these y values. Goes down to -infinity, goes up to -1, and then it picks up at 1 and goes to infinity. So the range is this. The period is the same as the period for sine, which is 2 pi. And because it's undefined, it has infinitely many vertical asymptotes at x equal n pi, again, where n is an integer. You can see these on the graph. So asymptotes here, I've shown at negative 2 pi, negative pi, 0, pi, and 2 pi. Now there's a couple other, for each cycle, there's 2 important points for the cosecant. Let's look at this one first. This point is a relative maximum. This value of negative 1 is a relative max, because in this little neighborhood, that is the highest y value. Where do they occur? Well, it occurs at 3 pi over 2, plus, of course, 2 pi times n, where n is an integer, adding the period. Gets me to the next one. The maximum value is, of course, the y value, which is negative 1. Now let's look at this point. This point is where the relative min occurs. The x-coordinate where it occurs is at pi over 2. And of course, to get to the next one, you add 2 pi, the period, times n, again, where n is an integer. The minimum value is 1. So those are 2 important points to know about. So let's see, let's underline them, the relative max and the relative min. And important what the y value is. And the function is odd, which means that the cosecant of negative x is negative cosecant of x, which means the graph is symmetric about the origin. You need to learn this graph and be able to graph it with showing the 2 points on each cycle and the asymptotes. Let's look at sketching functions of the form y equal a cosecant of bx minus c. Here, my example is y equal negative 3 cosecant of x minus pi. To graph functions in this form, we're going to graph its reciprocal function, a sine bx minus c, that you should be very good at graphing. So our first step is going to be to sketch the graph of negative 3 sine of x minus pi. For this graph, we know the period is 2 pi because b is 1. We know there's a phase shift of pi to the right. And we know the amplitude is the absolute value of negative 3, which is 3. So let's sketch that graph lightly first. So the shift is pi. So remember, well, let me make some tick marks here. So let's see, pi. And we need 3. Okay. So since the phase shift is pi, that means pi 0 is going to be a point for the sine. And then because a is negative, remember it's going to go down first. So at negative 3 pi over 2, it's down at negative 3, 0, up to 3, back down to 0. All right, so there's one cycle for the sine. Let's go ahead and sketch another one. So this is negative pi. So it's going to go up to 3, back to 0, down to negative 3, and back to 0. Okay, now we have 2 periods for the reciprocal function negative 3 sine of x minus pi. We want to get the graph of the cosecant. If the sine is 0, then we know we're going to have vertical asymptotes. So in this case, every time the sine is 0, here at negative pi, 0 pi, 2 pi, 3 pi, that's where your asymptotes are going to be. So we have an asymptote here, we have one on the y, we have one at pi, 2 pi, and 3 pi. Okay, so now that we know where the asymptotes are, we want to figure out the 2 points on each cycle. This point right here, this pi over 2, 3, we can see is a relative max for the sine function. That's going to be a relative min for the cosecant. And this point, which is, let's go ahead and label it, it was, let's see, 3 pi over 2. It's down at -3. That minimum point for the sine becomes a maximum point for the cosecant. So let's draw our graph. Okay, so we've got our points labeled. Next thing we want to know is what are the relative maximum points for the cosecant. Well, let's see where they are. This point is a relative maximum point, and this is a relative maximum point. What point is that? It occurs at -pi over 2, -3, and then this one is at 3 pi over 2. Oops, 3 pi over 2, -3. Okay, and those, for this 2 periods, those are the only 2 relative maximum points. Now, what are the relative minimum points? Well, for these 2 cycles, there are 2 relative minimum points. Let's go ahead and list those. This one is at pi over 2, 3. And this one is at 5 pi over 2, 3. So we have determined the easiest way to graph the cosecant is always to graph its reciprocal of sine, which you should be good at. And then once you get that, it's very easy. Every time the sine is 0, that's where your vertical asymptotes are. Find your 2 points for each cycle, and then sketch your graph. Remember, you approach the asymptotes. Once you have that, you can easily find your relative maximum and relative minimum points. You need to practice working these examples until you have mastered the skills and concepts involved. Let's take a look at the secant function y equals secant x. Recall that the secant function is the reciprocal of the cosine. So we're going to write this as 1 over the cosine of x, which means the secant will be undefined when the cosine is 0. And when is that? Let's see, undefined. The cosine is 0 at odd multiples of pi over 2, which is a way of saying 2n plus 1 over 2 times pi, where n is an integer. What's going to happen for the secant is that's where the vertical asymptotes will be. First, let's do this. Let's sketch our basic function y equal cosine x that you should be very familiar with. So let's see, remember cosine, 0, 1, pi over 2, 0, pi, -1, 3 pi over 2, 0, 2 pi back up to 1. And then let's draw another period to the left. So -pi over 2, this is 0, -pi, -1, -3 pi, back up. Okay. All right, so here's our basic cosine function. So since the secant is the reciprocal of the cosine, we're going to be able to get some points. First of all, remember we said that wherever the cosine is 0, the secant will be undefined. That's where the vertical asymptotes will be. So I can see that there's going to be a vertical asymptote at pi over 2, 3 pi over 2, -pi over 2, -3 pi over 2. Next, this point here on the cosine, 0, 1, well, the reciprocal of 1 is 1, so this point will also be a point on the secant function. And all these values of cosine between 0 and 1, the reciprocal of those values are numbers bigger than 1, and it approaches the asymptotes. So this is what that portion of the graph looks like. Here we have a point for cosine pi negative 1, well, the reciprocal of negative 1 is, of course, negative 1, so that will be a point on the secant. And all these values for the cosine between negative 1 and 0, the reciprocal of those values are numbers less than negative 1, and it approaches the vertical asymptotes as well. Here's one period for the secant. Let's draw another. Oh, I forgot this portion. Of course, reciprocal of 1 is 1, and then it approaches the asymptote. So here is 2 cycles for the secant function. You need to learn this graph and learn where the asymptotes are and those 2 points for each cycle. Let's look at characteristics of the secant function. First, the domain. Values of x are all real numbers except when x is equal to 2n plus 1 over 2 times pi, where n is an integer. That's another way of saying odd multiples of pi over 2 is not in the domain. The range would be the y values. If we look at the graph, we can see the y values go from negative infinity up to and including negative 1, and then it jumps up and goes from 1 to infinity. So that would be the range. The period is the same as the period for cosine, which is 2 pi. It has infinitely many vertical asymptotes, and they occur where it's undefined, which is x equals 2n plus 1 over 2 times pi. Again, same thing as odd multiples of pi over 2. So we can see our asymptotes are at negative 3 pi over 2, negative pi over 2, pi over 2, and 3 pi over 2. The next one would be at 5 pi over 2. For each cycle for the secant function, there are 2 important points. One is where a relative max occurs, and it occurs at the x value pi. The next one would occur 2 pi away times n. Again, n is an integer. And the maximum value is negative 1. Again, in this region, this is the highest y-coordinate. Here we have a relative minimum point. It occurs at x equal all multiples of 2 pi n. So one's at 0, the next one would be at 2 pi, negative 2 pi. Again, n is an integer. And the minimum value is 1. The function is even, same as the cosine, which means that the secant of negative x is secant of x. That's important. Let's underline relative max and relative min. And because it's even, that means that the graph is symmetric about the y-axis. It's important that you know how to graph the secant and know all where the asymptotes are and where those 2 points are.
The next step in our study of the trig functions is to define the inverse sine, inverse cosine, and inverse tangent functions. Let's start by reviewing the graph of the sine function. Okay, you can see I've drawn it here. Its domain is all real numbers. Its range is from negative 1 to 1. And our goal is to find an inverse for this function. Okay, it'll help you a great deal to think of these x values as angles. And so your sine function takes an angle, an x value, and spits out or gives out a y value, a real number between negative 1 and 1 that is the sine of that angle. What we'd like to do is find an inverse function that takes one of these real values, real number values between negative 1 and 1 and gives us back a unique angle. But there's a big problem. Notice that if I pick, say, 1/2, there are a lot of angles whose sine is 1/2. It wouldn't be a unique angle. And the term for this is not a one-to-one function. A one-to-one function doesn't have an inverse, so we have to do a little work to find an inverse function. We're going to take just a one-to-one piece of our sine function and work with that. Okay, so it might help to remember the horizontal line test from algebra. Right? Horizontal line test, horizontal line crosses more than once. The graph's not one-to-one. So we're looking for a little piece of the graph where when we draw that horizontal line, it'll only cross one time, anywhere we draw it. There are a lot of those pieces. There's this piece, there's a piece here, and there's a piece back here, and so on. It's customary to take this piece. It starts when x is negative pi over 2 and ends here when x is pi over 2. And this is the piece that we're going to work on. So let's draw this piece of this one-to-one piece of the sine function separately. We'll start here. This is negative pi over 2, negative 1. Here's the point 0, 0, and then the point pi over 2, 1. And then we'll draw our sine curve. So this is our function, y equals sine of x for negative pi over 2 less than or equal to x less than or equal to pi over 2. And we can see this is our one-to-one piece we want to use. Each of these angle or x values corresponds to one y or sine value. And furthermore, each y value corresponds to exactly one angle value. Since we have a one-to-one piece, we're ready to define our inverse sine function. So y equals the inverse sine of x is the inverse of our function y equals sine of x for negative pi over 2 less than or equal to x less than or equal to pi over 2. This function, y equals the inverse sine of x, has domain, a closed interval from negative 1 to 1. And range, negative pi over 2 to pi over 2. Okay, so our inverse sine function is going to take a real number in the closed interval negative 1 to 1 and return a unique angle in the closed interval negative pi over 2 to pi over 2. Okay, one word about our notation. I know this looks like an exponent, this minus 1, but it's not an exponent. It's just a notational device. We read this y equals the inverse sine of x. It's not an exponent. The definition of the inverse sine function tells us that the inverse sine of x is an angle. We're going to call that angle theta. In the closed interval, negative pi over 2 to pi over 2, whose sine, S-I-N-E, is x. So we can write theta equals the inverse sine of x. It's just an angle. And we know that theta is in negative pi over 2 to pi over 2, this closed interval. So let's picture this here. Right, this is our usual coordinate system where we look at the different quadrants. An angle of 0 radians would be drawn here, pi over 2 radians along the positive y-axis, and so on. If angle theta is in the closed interval negative pi over 2 to pi over 2, then where could theta lie? Well, here's negative pi over 2. There's pi over 2, so it can be anywhere in quadrant 1 or quadrant 4. It could be along the positive x-axis, and it could be on either side of the y-axis, the positive or the negative. Okay. It would help us a lot to make a table that'll help us sort of track when x is a certain number, where does the terminal side of theta lie? Okay. So what are our choices? X can be negative 1. Remember, our inverse sine function has domain negative 1 to 1, that closed interval, so the smallest is negative 1. Okay. All right, well, where would that be? That would mean it was along the negative y-axis, the terminal side there. In that case, we actually know the angle right away. It's going to be negative pi over 2. All right. Anywhere in the fourth quadrant, the x is going to be, it must be a negative number, so we do from negative 1 to 0. Notice those are not allowing equal to, just an open interval. This is going to be in quadrant 4. If x is actually equal to 0, it also corresponds to theta equals 0. That's on the positive x-axis. X might be between 0 and 1, and that's going to make the angle have its terminal side lie somewhere in quadrant 1. And the last choice is x could be 1, in which case the terminal side lies here on the positive y-axis. And we know in that case that the angle would be positive pi over 2. I think you'll find this chart very helpful as you look at these next examples. Let's practice finding exact values using our inverse sine function. The first example is to find the inverse sine of positive 1/2. So remember, we're looking for an angle. We have to decide where that angle might be, and we know that its sine is positive 1/2. Okay. So in this problem, this is our x, and we can see it's positive 1/2, which is between 0 and 1. So we're looking for an angle in quadrant 1. Okay, in quadrant 1, the angles are positive and acute. And let's look at this x value more closely and see if it'll help us figure out which special angle is the answer. Okay. The sine of pi over 6 is 1/2, so there you go, that's your answer. The positive acute angle in quadrant 1, whose sine is 1/2, is pi over 6. Let's try a second one. This time, x is negative. It's between negative 1 and 0. Okay, so that means it's going to be, its terminal side is going to be somewhere in quadrant 4. Okay, it needs to be a negative angle in quadrant 4 because if you remember, the inverse sine function's range is negative pi over 2 to pi over 2, so we're looking for a negative angle. And I think we might want to use a reference angle to help us figure this out. Remember, a reference angle is a positive acute angle. We hope this is one of those special angles we know. The sine of pi over 4 is 1 over the square root of 2. So our reference angle is pi over 4. Okay, so let's just look at the angle and make sure that we pick the right one. We want a negative angle in quadrant 4. The reference angle is pi over 4, so this is actually that angle negative pi over 4. Okay, last one. Inverse sine of negative 1. Okay, negative 1 is one of these sort of special cases. The terminal side of theta will land on the negative y-axis, and theta has to be negative pi over 2. Let's turn our attention to defining the inverse cosine function. As we look at the graph of our cosine function, we see that again it is not a one-to-one function. So we need to find a one-to-one piece and define our inverse on that piece. Again, we have many choices, but the customary choice is to take this first piece from 0 to pi, and it's first from the origin, so that makes sense. Okay. We'll draw that one-to-one piece here and examine it more closely. We have the point 1, 0. or 0, 1. Pi over 2, 0. And this one is pi negative 1. We're going to draw our cosine curve here. This is the function y equals cosine x, 0 less than or equal to x, less than or equal to pi. And we see that it is in fact a one-to-one function. We're ready to write the definition of the inverse cosine. Okay. So y equals the inverse cosine of x is the inverse of the function y equal cosine x on the interval from 0 to pi, closed interval. The inverse cosine function has domain negative 1 to 1, again a closed interval, and range the closed interval from 0 to pi. So this inverse cosine function will take in a real number from this interval and give us back an angle in the closed interval 0 to pi. Let's use our definition of the inverse cosine function to help us find exact values. The definition tells us that the inverse cosine of x is an angle, which we'll call theta, in the interval, closed interval from 0 to pi, whose cosine is x. Okay, so we're going to write this again a little bit differently. Theta is the angle theta is the inverse cosine of x, and we know that 0 is less than or equal to theta is less than or equal to pi. Okay, so where will we find the terminal side of such an angle theta? Well, it has to be from 0 to pi. 0 to pi, that's this part. Quadrant 1, quadrant 2. The positive x-axis, the positive y-axis, or the negative x-axis. Okay, let's organize the information that we have. What are the possible values of x? Well, what's the domain of our inverse cosine function? It's the closed interval from negative 1 to 1. Okay, so if we have x equal to negative 1, then the terminal side will lie on the negative x-axis. And that is the angle theta equals pi. Okay. X can be something between negative 1 and 0. Okay, so that's a negative number that's going to lie, means the terminal side will lie in quadrant 2. X could be 0, in which case the terminal side lies on the positive y-axis. And so that means the angle theta is pi over 2. We have two more possibilities. If x is between 0 and 1, then the terminal side is somewhere in quadrant 1. Or x could be 1, and that means that the angle lies on the positive x-axis. And that would be theta equals 0. Let's look at some examples of finding exact values of inverse cosine function. Here's our first one. Find the inverse cosine of 1 over the square root of 2. Okay, so our x value is 1 over the square root of 2. This is between 0 and 1, so we know that we're looking for an angle in quadrant 1. In quadrant 1, our angles are acute positive angles, and we just need to try to figure out if this is one of our special angles that we know. That's right, cosine of pi over 4 is 1 over the square root of 2. So the angle in the first quadrant, whose cosine is 1 over the square root of 2, is pi over 4. Okay, the second one, the inverse cosine of negative 1/2. So in this case, the x value is negative 1/2. That's going to be in this interval, negative 1 to 0. That means the terminal side of our angle theta is in quadrant 2. Okay. Okay, so we need to figure out which angle that is in quadrant 2. We're going to use our reference angle to help us figure that out. The reference angle is the angle it's a positive acute angle whose cosine is 1/2. Right, the reference angle should be pi over 3. Let's draw a picture of the angle that is going to be our answer. It's in quadrant 2. The reference angle is pi over 3. And here's the angle we need. How do we figure this out? So it's pi minus our reference angle, or 2 pi over 3. Okay, one more. The inverse cosine of 0. Well, when x is 0, then we know that the terminal side of theta lies on the positive y-axis, and that makes our angle theta pi over 2. Let's now try to define an inverse tangent function. Okay, so the graph of the tangent function is shown on the board, and we see again that it is not a one-to-one function. So in order to find an inverse, we need to choose a one-to-one piece. Actually, each of the pieces is one-to-one. Any will do, but the customary choice is this piece that runs from negative pi over 2 to pi over 2. Notice that at the ends, those are vertical asymptotes. So we're going to choose the open interval from negative pi over 2 to pi over 2 to restrict the x's to. Okay, we'll highlight it here, and now let's draw it separately so we can look at it carefully. We have vertical asymptotes at pi over 2. And at negative pi over 2. And then we just have this one piece. And it's definitely a one-to-one piece of the tangent function. And we've restricted the domain to this open interval to get a one-to-one piece. We're ready to write the definition of the inverse tangent function. Okay. Y equals the inverse tangent of x is the inverse of y equals tangent x on the open interval negative pi over 2 to pi over 2. And this inverse tangent function has domain all real numbers and range the open interval from negative pi over 2 to pi over 2. Let's talk about using the inverse tangent function to find exact values. So from our definition, the inverse tangent of x is an angle, which we'll call theta, that is in the interval from negative pi over 2 to pi over 2, an open interval, whose tangent is x. And we can write this a different way. The angle theta is inverse tangent of x. So again, this is just an angle. And we know that negative pi over 2 is less than theta, which is also less than pi over 2. So let's look at where we find angles theta that meet this criteria. Okay, so negative pi over 2 to pi over 2 is here on the right side of this. It includes the first quadrant, the fourth quadrant. It includes the positive x-axis, and that's it. Because remember, this is an open interval, and the tangent is actually undefined at both pi over 2 and negative pi over 2. Okay, so we'll organize our information in a chart. If x is a negative number, then the terminal side of theta will lie in quadrant 4, here. If x is equal to 0, then the tangent of theta will lie on the positive x-axis. And that means that theta is 0. And the only other possibility is that x is a positive number, and that would place the terminal side of theta in quadrant 1. Let's look at some specific examples of finding exact values of the inverse tangent function. Okay, so our first one, inverse tangent of negative 1 over the square root of 3. So x here is a negative number. And whenever x is a negative number, the terminal side of the angle theta we're trying to find will be in quadrant 4. Okay. Right, that's the tangent there of one of our special angles, so let's see if we can find a reference angle. Okay, the tangent of pi over 6 is 1 over the square root of 3. So our reference angle is pi over 6. And we'll sketch a picture to make sure that we give the right name of our angle. So our angle theta is a negative angle in quadrant 4, and the reference angle is pi over 6. So here is the angle we need. That's right, it's negative pi over 6. Okay, the inverse tangent of 1. Okay, so we look at our chart to help us out. 1 is a positive number, so that tells me the terminal side of theta is going to land somewhere in quadrant 1. Okay, in quadrant 1, what's the special angle whose tangent is 1? Right, pi over 4. And we have one more. Inverse tangent of 0. Whenever x is 0, the terminal side of theta lies on the positive x-axis, so the angle is 0. Let's look at the instructions for this last group of examples. Use a calculator to approximate each of the following. Give your answer in radians. Round to 4 decimal places as needed. Okay, well, I've already worked these out with my calculator, but I'd like to talk to you about some helpful tips. The first thing is notice that you don't really have any other way to work this problem except for the calculator approximation, because this doesn't remind me of any of the special angles that we know. Okay, so how do we get this number? Well, this is important. Our answer should be in radians, so make sure your calculator is in radian mode. Where's the inverse cosine button? Usually it's the second button on the cosine key. And if you can't find it, be sure to look in your calculator instruction manual. Okay. Type in inverse cosine of 4/5, and then look at the answer on the screen. Round it off to 4 decimal places as needed, and that's your answer. And I've given you a couple of other ones to try. Make sure that you practice, that you learn how to use your calculator, and that you can get these rounded answers.